along with Dr. Sarup Yogi. It's very pleasure for us that today we have Professor Devnan Jana with us, and he will be giving the talk. And before that one, just as a small introduction or our speaker, Dr. Devnan Jana, MSc, PhD from Raman Research Institute, Bangalore. Is a professor of physics in University of Calcutta since 2012. He was a visiting fellow in CCMS, NTU, Taiwan during 2003-4. His current research is focused on defect studies in annealed and nanoannealed ion irradiated zinc oxide material, density functional theory in 2D materials, and photocatalytic activity towards degradation of different dyes. He was elected as a fellow of West Bengal Academy of Science and Technology, WAST. In 2015, he was awarded Distinguished Scientist in Physics by Venus International Research Award, VIRA, in 2017. He was also recognized by NGO for Popularization of Science Education in 2014. He has more than 160 papers in national and international peer-reviewed journals. Along with his distinguished collaboration, he had written 4 review articles, and one of his work in ZNO, and also just it is highly acclaimed by material science researchers. With his able guidance, 12 students have already obtained PhD degree from University of Calcutta, and about 8 to 10 students are working with him to finish their PhD research work. Several science lectures have been delivered by him to various schools, colleges, and also universities. So, sir, we are very happy and we are fortunate that Professor Jana will give us a talk, and the topic which have been given by him, a tight binding approach to Dirac materials in carbon fabric. So, sir, very fortunate and very good opportunity for us. Over to you, Professor Jana.
Okay, thank you for kind introductions. So I have been associated with this university for last couple of years, and it's really an honor to me that I have been given an opportunity to interact with the young budding scientists in our area, and I hopefully will be able to give some directions in the coming research areas in 2D materials. So with this thing, let me start with that my presentation. So is it visible?
Yes, sir, visible, sir.
Yes, okay. Thank you. So as I have told you that I'll be talking about some electronic structure calculations by a specific approach. So my topic is condensed matter physics, and this is a very rich area. One can actually work via the experimental area, also by the theoretical area. And I will give you a kind of a hint towards how to calculate some analytical calculations via this method. And this method had been there in the condensed matter physics for last few decades. However, in recent times, this has been kindly noted by the researcher in material science community to match this kind of result with the most popular DFT calculations. So with this thing, let me go to my the presentations. So I have been working in these particular areas for a couple of years, as have been already kindly introduced by Professor Sorkar, and I'll not go into the details of this thing. And what I plan to do is something related to the tide binding calculation. And I note that some of these slides and other things you might see in my previous lecture. However, I will try to give some kind of hint towards how to apply this in real solids. And this is a very interesting area, and most probably we can do some kind of contributions in this particular area. So I have been planning that I will talk about some basic introduction to Dirac materials. Then we'll very well-known tide bending calculation, which is done in our MSc class that I will talk about you, and another advanced courses classes that is the tide bending calculation of single layer graphene. So armed with this calculation, now we'll go to slowly to the research area where we will show that how to calculate the band structure via this method. And in this procedure, I will try to show some of these proposed new materials which have been there proposed my students and collaborators in the last few years. And though some of them have not been fulfilled the criteria of completely synthesized, because we know that there are lots of problems with the synthesis procedure, but at the theoretical base values, we'll try to show some of these things. And who knows, maybe in near future, this kind of material must be synthesized. So let me start with this very basic idea that this was the famous question was asked by Niels Bohr and to Professor Dirac. What are you working on, Mr. Dirac? So Paul firstly replied that I'm trying to take into the square root of something. Question is, what is something? That was something related to energy. And this way he actually talked about the so-called the square root of px square, py square plus m square. So we are talking about in the unit where this velocity of light in free space is equal to 1. So he was trying to write down the square root of this energy with these linear combinations of these Pauli spin matrices. And he was very successful, which actually starts the arena of the relativistic quantum theory. Because you remember, the Schrodinger equation is a non-relativistic theory, and that's why we started with this relativistic spin orbit coupling, all the sorts of mass variations, hyperfine, fine structure, all emerges from this famous Dirac-Hamiltonian. So let me again go back to our college days that we were talking about something like tide bending simple cubic solutions. And this was the typical energy eigenvalues. All we remember this thing, that is the on-site energy epsilon minus this hopping energy, that is twice T cosine kxa plus cosine kya plus cosine kza. So you can calculate this effective mass according to the different K points in the Brillouin zone, and which is the famous like this thing. If this hopping is very large, then this mass will be very small, and we call that this narrow bands must have this high effective mass because the bandwidth is also small. So in this way, we can go to the other tide binding calculations for the face-centered cubic, because the position of these atoms are different compared to the cubic system. So we get a different expressions, which is shown it here. And we can also show the different Brillouin zones and this band structure calculation. And all the effective mass and other things can be calculated. For example, the important quantity in our electronic structure calculation is the quantity called density of states, meaning the number of states lying between the energy interval E and E plus D per unit volume. And this is a very important quantity in calculating all the electronic, optical, and the magnetic properties, because the density of states exactly at the Fermi surface play a crucial role in determining the various properties of the solid. So it is essential to know this, how does density of states vary with this thing. So this is a typical picture of this density of state variation for FCC system. And we can also see this different Brillouin zone with the energy pocket. You can see this the Fermi structure topology. It's not very simple. It's a very complicated, open, closed, all these kinds of things are there. And that actually gives rise to the various important properties related to Hall coefficient, related to transport properties, all sorts of peculiar and anisotropic properties originate from this topology of this Fermi surface. Now we come back to this question of what are Dirac materials. Dirac materials turns out to be one of the complex and functional nanomaterials in the new arena, and where there is a surface called the Fermi surface. We know that thing, these two lines, that is from the band conduction and valence band, they two intersect. So there are few points in this material where the changes are quite strong and the band actually intersect there. So when using the conventional material, we talk about a various surface area. But in this particular class of material, there is only one point through which all the transport property will be controlled. So I will go to the details as you go on. But for the time being, we just remember that this is a unique point from which we can control the electronic properties. And here is a snapshot of these different properties of this conventional system. So we are showing here the E versus K curve, that is called the band structure curve. So metal, we know this Fermi level lies here. The insulator, there is this gap, and gap is more absolutely greater than almost like 4 eV. You can also think of some kind of as a wide band gap semiconductor too. And this is a conventional semiconductor, and this is the semi-metal where these two bands touch with each other. So we'll see these properties as we go on. And as I was telling, there is this most important contrasting behavior between the insulator and metal and the Dirac material have been depicted in this particular view graph. So we plot in y-axis and x-axis, that is the crystal momentum. That's the quantity we often use in our solid state physics, because the linear momentum is not the eigenvalue of the block tight binding wave functions. So we talk about so-called the crystal momentum, because the momentum also carried by the lattice. So if you talk about the metal, so as I have told you, because of this large surface area, the particle and hole excitation can take place over a large area. However, because of this shrinking of this point to a single point, the particle hole excitations actually occurs in only one point. And you know, remember in the insulator, that's very tough to do these excitations. So that's why there is no conductions in this thing. So if you look out the other way of looking this thing, earlier we looked about the band structure. Here we talk about the density of states. So if we plot the density of state as a function of energy, in the case of metal, where we have partially filled band, there is a finite density of states at the Fermi energy. However, in the case of a semiconductor, where we have a one field gap and there is a gap exactly at the Fermi energy, the density of states looks like this. And graphene, which is one of the foremost Dirac material, which shows this particular picture, we can either call it by zero gap semiconductor or a zero DOS metal. So the gap exactly at the density of states, that's density of states is zero. And we'll show that there is a V-shaped density of states lying with this. So armed with these basic introductions, we'll again do some another important calculations, which will help us to understand the basic physics of graphene, that is how to calculate the important properties of graphene. So we know that Dirac equation, the massless limit, will have a linear dispersion relation. So the linear dispersion relation is shown it here. And we have these two kinds of fermions. We call it one fermions residing in sublattice A. Here we have shown it by the blue points, and another by the sublattice B. Remember that this hexagonal lattice is not a Bravais lattice. So we have to choose an appropriate unit cell to calculate this thing. Then let us talk about another simplest system, which we again have done it for the benzene system. So here we have this kind of pi bonds, And the unit cell, as I have told you, consists of 2 atoms per unit cell. It's a rhombus. This is not the usual hexagonal ring. And we did these calculations, that is psi m r equal to cmn phi nr, and this is the orthogonal property. So I remembered this 1, 2, 3, 4, 5, and we can write down this 5 cross 5 matrix. It is actually 6 cross 6 matrix because we have started with 0. So we can calculate this thing. And these are the kind of hopping matrix element because there is only nearest neighbor hopping and the onside. And it is easy to see that we can find out the eigenvalues E0, E1, E2, E3 like this. And if you look out further, we can also look out this transitional symmetry associated with this particular hexagon, and that is the honeycomb lattice, and the Rn is equal to Na, and these boundary conditions give you K is to be discrete. Remember, the length is 6a because 1, 2, 3, 4, 5, 6a, and where this m can vary from 0 to 5, and if you can invoke these wave functions, we will have this particular property. And you can see that exactly like the linear chain, we have this K equal to epsilon plus twice T cos K. Remember that our Hamiltonian is Hermitian. Now, if you look out another interesting feature, invariant of this tight binding model, where we have this kind of structure that is a linear chain, and then we can have a simple metallic structure. This is also a textbook problem. And here E max is epsilon minus twice T, and the E minimum is epsilon plus twice T. So the bandwidth is basically your 4T, and we can calculate the density of states, which you can see that sign looks like to diverge at the 2 ends, that is maximum and minimum ends. And so this is basically a metallic state, and we do not have any insulating state. However, you can have an insulator to semiconductor if you change this thing with a different on-site energy. So if you do this calculation, I am not going to do calculations, and you can see that immediately there is a possibility of having a window of gap and a insulator to semiconductor tension is possible. So depending upon the value of on-site energy, you can actually have this excitation greater than the G, that is the gap between this, and we can have this the electron hole excitation. So these are the things, simple things, which will be used later on to introduce the graphene electronic structure. So remember, graphene has 6 electrons, 4 valence electrons. This has this particular property, that is sp2 bonding, and there are 2 kind of bonding electrons, sigma bonds and pi bonds. Pi bonds electrons are moving across this thing, so they allow conduction. However, the sigma bonds actually has a exceptional structural rigidity. So these are the information which have been passed to our chemistry researcher to calculate that thing. But before we start the calculation, let me spend some time that why these 2D materials are rising star for future application. First of all, they are reduced length in the vertical directions, that is at the order of 1 nanometer, which helps us to make the device as small as possible for various optoelectronic properties. Secondly, the Coulomb interaction, which is the fundamental interactions in 2D system, is significantly reduced. And as a result, we greatly enhance the many-body interaction, which are the sole agency for emerging many properties. For example, the Coulomb interactions between electrons and holes in this particular 2D system is several hundreds of MeV. So roughly, it is 1 order of magnitude stronger than that in 3D. So thirdly, different degrees of freedom of these quasi-particles in 2D system can emerge. For example, there are called valley, orbital, spin, topology, layer, many sorts of kind of attributes or degrees of freedom can trigger many important states and their application. So that's why people are actually interested in this 2D material to work on. And there are several more. I'm not going to the details of this thing, and interested readers should go to read this particular review, and that's very interesting, and many new more ideas you can think of. And there are really very challenges for the young people how to use this practical application for 2D materials. Most of the 2D materials have this fundamental property of lacking a poor long-term stability. Although they have a fascinating properties, but whether they are stable for a long time, that has to be tested. And secondly, their low carrier mobility and the low absorption rate of single layer 2D materials, that is a problematic for any application related to optoelectronic property. Thirdly, which is very important, the weak magnetic interactions as well as the low conductivity of such magnetic material in 2 dimensions, because of their localized orbitals, they are very difficult to tackle in calculating the magnetic property. Though there are few techniques and emerging areas have been identified, people are still working on this thing. And fourthly, the low-cost growth of various 2D materials with controlled quality and doping, and of course, the scalable integration of channel, contact, and dielectric material. All these things needs many more time to think that what particular way we can do these things so that we can have a very stable, low-cost growth of these 2D materials. But I should say that in the last couple of years from India and other things, there are new emerging 2D materials are coming off, and hopefully this problem will be there. And I will show this slide that there is a very interesting progress in the synthesis of novel 2-dimensional van der Waals materials. And this is very recent article, last year article. So I will urge the researcher who are interested in this area should go through it. And before we start the calculation for graphene, let me at least tell you something which is very important, that what are the main difference between the graphene and traditional 2D material. Most of these traditional 2D materials have a finite gap, but graphene, as I have told you, will show it immediately there is a nominal gap of 0. So the study of electron and hole motion through a semiconductor, that actually very interesting, because we do not have to do the usual 3-dimensional way of doping. For example, there are other kind of effects from basic point of view called the Klein tunneling. This is a tunneling where it occurs basically in a relativistic system, and that can be seen even in graphene. So graphene dispersion is indeed chiral, and most of these cases, our 2-dimensional dispersion relation is of the order of quadratic dispersion. However, as I have told you, that this has a linear dispersion relation. And this is very important in many impressive properties of this graphene. There are other few important kind of differences. I'm not going to these things because we have to do some calculations, and how to do that thing we'll show you. So let me start with this tight binding calculation. First, we have to identify the unit cell which repeat, and we can generate this thing. Remember, I repeat again that hexagonal lattice does not have any, it's not a Bravais lattice. So that's why we have to think about a rhombus having 2 different sides, A1 and A2, with this thing. And this is tau 1 and tau 2, which I have shown it here. And depending upon this, the translational vector, that is n1 times A1 plus n2 times A2, where n1, n2 can take value 0, 1, 2, and the reciprocal k is k1 plus B1 plus K2 into B2, and the reciprocal lattice vector Bi must satisfy this orthonormality condition. Given this condition, we can, however, generate, because you can always have tau1 plus R and tau2 plus R, where R is like this thing, so that we can generate the whole lattice. So this is a peculiar thing to say, that these lattice vectors, which I have designated at the two sides of this rhombus, are not orthogonal. So given this fact, you can actually now go to construct this the two-dimensional reciprocal lattice vector, which I have shown it here. This is 2 pi by A, 2 by root 30, and B2 like this. By the way, we can also identify the other important key points in the Brillouin zone, which is gamma point, which is the most symmetric point, and the other M and K. That's also another logic, because the reciprocal lattice of an hexagonal lattice is an hexagonal and with some rotations. Okay, like BCC's reciprocal is FCC. So this is the one type of crystal for which the reciprocal lattice is, apart from the simple cubic, this is hexagonal. So we can generate the various K points from this thing, because once you know the reciprocal space, then what we have to know, we have to write down these various, these are the points which I talk about, K, K dash, gamma is the most symmetric point. This is M, and this is K and K dash, and this is B1 and B2. So these are the off-diagonal element, which I have shown it here. And this is the phase factor, which coupled with this A1 and A2. So given this thing, we can now calculate their Tk, which is T times 1 plus e to the power twice pi ik, and 1 and minus e to the power minus twice pi ik, 2. So once you give that thing, this is very simple to diagonalize this Hamiltonian, and we get this Hamiltonian, and this is the structure of this energy dispersion curve. And you can see that there are these points K and K dash. They are actually 6, but actually there are 2 which can be related by other reciprocal lattice vector. We can generate them. So around this point K and K point dash, these are called the Dirac points. The band touches each other. That's actually band is given to 0. So given this dispersion relations to be 0, and this Fermi level resides on their thing, we can calculate this factor easily. Now the question is that what happens near this Dirac point? So we can extract some low energy physics from the Dirac-like Hamiltonian. So we expand around a small Q vector around this Dirac point. This K is written as the Taylor series expansion of this K dash plus capital K dash plus Q dash, and you just add this phase factor like this thing, approximate by the exponential factor, you will get this Tk, that is the hopping parameter, looks like a very simple minus 380 by 2 into Qx minus Iqy. So you can rewrite this Hamiltonian with the identification of the Fermi velocity H cross Bf equals to minus 380 by 2, and that gives rise to the determinations of this Fermi velocity. So given this lattice constant and the hopping parameter, that is around 2.7 electron volt, you can calculate this Fermi velocity. And what happens to the structure of this Dirac-like Hamiltonian? You can see that thing, you can approximate, and this can be written as H cross Vf Q dot sigma. And here lies this analogy which I shown in the beginning of my talk, that this linear dispersion relation. So this around this Dirac point, we can approximate the Hamiltonian to a Dirac-like Hamiltonian. But remember, this Fermi velocity again is 2 orders of magnitude less than the speed of light in free space. So in that sense, it is not a quite relativistic, it is the analogy which we are pursuing here. So if you look out this particular picture, as I have told you, this is the typical quadratic dispersion relation, and this is the dispersion relation in graphene near the Fermi Dirac point. Okay, if you go beyond the Dirac point, of course, the structure is different. And here is again a simple distinction between the different kinds of fermions. So if you have a Schrodinger fermions, that is quantum non-relativistic permeance. So we have a non-relativistic dispersion relation. You have a ultra-relativistic Dirac particles. Then you have this Hamiltonian C times sigma dot P. However, you have a massless Dirac permeance. Then H is the VF sigma dot P. So that's the kind of difference we have in our mind. So the next important question is this linear dispersion consistent with the experiment? The answer is of course yes, because there is this Nobel Prize in 2004 given to scientists. And what we have seen in this RPS data, that is called the angle resolved photoemission spectroscopy, you can see this crossing of these two linear bands very accurately. So it is experimentally proved. And if you are again go to the local probes by STM and extended magnetotransport property, also you can see this picture more clearly. So it has been experimentally verified, and we can actually go through this thing. I'm just skipping some of these slides because time is short here. So now we are trying to go to the typical calculations, what we are doing via this type binding. So it is not that there are only graphene is the Dirac material. There is a plethora of 2D material like silicon, germanium, and all sorts of elemental or heterostructure. They also possess this Dirac cone. So the question is there, why are Dirac materials rare? It has been shown explicitly via a tight binding model. First of all, the hopping integral should form a triangle. So if T1, T2, T3 are the next nearest neighbor, next nearest, and next nearest neighbor hopping parameters, then they must satisfy this identity. Moreover, those 2D materials which have two atoms of same species in each unit cell, they also have to satisfy an additional this criteria. So if these two criteria are fulfilled, then we can have this Dirac cone. And apart from them, there are also some symmetry and parameters involved, because there are a number of parameters and the number of variables should match with that thing, and that should actually count the existence of Dirac cones. However, I have a very simpler way also to by the degenerate perturbation theory. If you go on, because there are H11 and H12, H21, H22. So if H11 and 2 are equal to H22 equal to 0, then they are degenerate, so they can meet to a single point. So there is another simpler way to do that thing. So I'm not going to the details of these things are already there in the literature, but some group theoretical argument based with the typical symmetry that can give to a particular lattice, there is a possibility. But often it is very difficult to tell just from the lattice structure unless we perform the appropriate symmetry operation. So with the help of symmetry and the group theoretical help, one may possible, because I do not know explicitly, but it is possible. What we do is basically we do some first DFT calculations, and then we can argue something. So we started with this tetragonal graphene, so-called T graphene, which has this particular property, and it has been shown in 2012 that T graphene has this Dirac-like permeance and other things. Okay, so we choose this. This is the relaxed structure of T graphene. The space group has been written P4MM. Unit cell contains single C4. There are 4 carbon atoms there. All these things are optimized from the Dirac theory. Then actually we can do the calculation with the typical this intra-square and inter-square. So we have used 2 hopping elements, and we can calculate these dispersion relations, and we can see that these DFT calculations and the tight binding approximations, this is the equations obtained from the pi electrons in this particular thing, and we can plot that thing. It is interesting to note that there is this matching of DFT result and the tight binding calculations. So this is the first opportunity we have used this tetragonal graphene system, and we have obtained this calculation. Later on, we have also used to calculate the band tuning of this particular. We can add this a flux to this thing, and I think Otonu is there in the audience. So we started this calculation with the help of a new technique called the real space decimation technique. I am not using the word called renormalizations because that's a little bit different meaning, although it started with that thing. And there are already used in this decorated lattice for a couple of years. And we use this thing in this particular sheet and nanoribbon with this introduction of this pile substitution of flux and with this decimation technique to reduce this interacting system to a linear one-dimensional chain. And we can see that this flux actually introduced an opening of a band gap. And this is the first opportunity that flux in this particular graphene system, where it is interesting to note that flux can induce a band gap, and this is a direct band gap. So you remember that band gap is an essential factor in this graphene system because graphene has zero band gap. So if you would like to use this graphene, any nano variants or any other like quantum dot or another thing. So people try to open a band gap because that's very suitable for imparting as a kind of typical device because the current control is not possible without having a band gap. So further, we have also used this narrowest armchair T-graphene nanoribbon that's known as NAT GNR. So we have obtained these tight binding calculations here and also the DFT calculation, and this actually matches very good in this particular system. And then we use this technique to open to another new system called the graphene, where we use the triple linkage in this particular graphene system. And fortunately, there are many variants like alpha T graphene, beta T graphene, gamma T graphene that has been emerged in this particular area. And this gamma graphene has been recently synthesized. So we hope in near future, maybe our calculations will be very helpful. And we first check their thermodynamic stability, that is dynamical stability, thermal stability, and the mechanical stability. So these are the kind of phonon dispersion graph, and you can visualize there is no negative frequency, and the structure after these so many time steps remains almost same. And also further, the mechanical stability also helps us to do that thing. And here we have also shown that thing, that is this variety is dynamically stable. And once you have this tetragonal graphene, we can further go to the calculations of this thing. So here we show this typical 4 types of thing, T1, T2 we have introduced, and we can find out by solving these tight binding equations, Schrodinger form with these eigenvalues, and you can see the Fourier symmetry associated with that thing. And this is very interesting that although we have obtained the result from the DFT, we have also obtained from the tight binding, and this tight binding result tells us the beauty of these calculations. And then we move further to another important system that is called the S-graphene. And by S-graphene was already introduced into the literature in 2014. It has been obtained by this famous structure searching method known as Calypso. And the calculation was done by the FAST, that is Vienna adopted that ab initio simulation package. That's the most popular simulation package and they showed these two Dirac cone. Question is that how good is this result and why there is this point Dirac point. Most of the cases there are other K points did occur. This is a little bit away from this thing. So first question is that is there any analytical way to tackle this thing? The answer is yes. So we started with this initialization of real space decimation technique, identify this unit cell, and we started with these calculations, and we have denoted the various hopping parameters, and the shaded color things had been decimating out. So we get this thing. Again, this is further decimated. So we get this thing. So you can do this thing under the condition this energy is approximately equal to epsilon, and the hopping parameters is normalized in this particular fashion. And as a result, this T dash, TW dash are actually have this particular property with the connection of the other hopping parameters. So once you do that calculation, you will obtain finally the dispersal relation, which have been shown it here, and we exactly get these Dirac points A and B consistent with our DFT results. So we have been able to identify the positions of the Dirac point, which was shown by the DFT. Not only that, question is that can I open a band gap either A and B or vice versa or two? The answer is yes. By suitable choosing of these hopping parameters, we can actually control the this Dirac point, and I have shown it here with these following conditions of these hopping parameters that we can actually do that thing. So you might ask that in the experiment situation, how do you control hopping? So remember that thing, this calculation is meant for the freestanding S-graphene. The experimental situations, of course, has to have a possible substrate and an environment. These calculations are done for zero temperature. So possibly controlling these different ambient conditions, we can assume that there is a possibility of changing that hopping in a particular real experimental situations. Okay. So we can show that this opening of band gap and the nature of this Dirac cone into this particular thing. So next we are going to another interesting aspect which have been done in the year 2021. This is the predicted new structure from our group 816 graphene. This is a square lattice two-dimensional nodal line. So till now we have discussed about the Dirac point. Now it is a Dirac line. So how does this interplay occur between the square symmetry and the Dirac hallmarks? So we propose this particular graphene, which have been checked by this another evolutionary algorithm to specs, and we have seen that there is inversion, mirror reflection, and the time reversal symmetries are preserved. Not only that, the structure is dynamically, thermally, and mechanically stable. The plane group actually is P4 mm, and the lattice constant, the optimized lattice constant, that is around 7.35 angstrom, and the unit cell consists of something like 16 carbon atoms with a combination of sp and sp2 hybridization. And here is one simple comment before we start the calculation. Recently, we have seen in archive the same structure has been proposed by a group which has been shown as sun graphene. But I do not know that structure was there for around, we are the first to propose this structure, and they have cited our other works, but not this one. This is very unfortunate, but we contacted them that this work has already been published in Physical Review B. So then they said, okay, we'll do that thing. So they actually have checked our calculation. It is nice to know that they have obtained the similar thing, and they have further gone beyond not only the monolayer, but the bilayer thing, and they calculated some transport properties on the bilayer. So what is the structure look like? So it is also like the S graphene, 2 Dirac points, and I'm not going to the details of this RSDM approach. Analytically, we can again show that it matches with the prediction of this uh, DFT, and I have shown it here a 3-dimensional energy band structure where this has a nodal line. So instead of a point, there is a nodal line here, which have been shown in this particular thing. And this structure also poses some topological aspect, which I am not showing the results, but it has this a topological aspect. It is not trivial because it has also some flat band, and that flat band has a interesting property which can be judiciously utilized in the topological aspect of that thing. Later on, we move further to another interesting properties of another proposed far graphene, and this far graphene has been was proposed first by the Oganov group in Russia and in nano letters, and we try to see that features of these Dirac cones if we dope with boron and nitrogen. So we started with this particular, it has only one Dirac point, and we proposed several structure A, B, C, D, E with this boron and nitrogen doping. Remember, boron and nitrogen, they lie very close to carbon. They have similar radius, ionic radius, and if we dope it in the carbon network, most of these things, this structure looks stable. Furthermore, if you dope simultaneously the boron and nitrogen, they do not change the total number of electrons in the system. So that is isoelectronic with the pristine one. So given this kind of facilities, we will move to the calculation of band structure. We find out of these 5 structure, only 2 structure has this a possibility of opening a band gap. And further, we can see that this is the other 2, D and E. So they also have this band gap. And then we use this RSDM structure that some of them has a cone and some of them there has a gap. So is it possible to explain that why the other does not produce that gap? So it turns out that if we use this judicious choice of these hopping parameters, and with this decimation technique, that's the unit cell which is highlighted in the dashboard. And there are T1, T2, T3, and T4. These are the hopping parameters. And once you do that thing, it is a simple thing to look out this structure, the Hamiltonian structure, and we find out these eigenvalues like this thing where we have shown it A, B, C, D, and other things. And we have obtained this particular dispersion relation. And finally, more interestingly, being a graphene family, we can also reduce this Hamiltonian to the particular graphene-like form that is shown it here in the 2x2 matrix form. Besides, we have also verified that near this point, near this Fermi energy, the DFT result and the tight bending result almost match with that thing. So this gives you a very nice idea that how this kind of technique, analytical tight bending tailing, which can actually show you how to calculate the position of the Dirac point or Dirac nodal line, and this calculation will further be adapted to either in the optical properties or in the transport properties or many other physical properties. I have not shown here other properties, but I have focused on the electronic band structure calculations. and how this technique can be given to them. So I am almost towards the end of my talk. So these are the another important class of problem with the acetylenic bonds in typical square graphenes, where we have again used both DFT and tight binding result. And furthermore, we have used also the calculation of IV characteristics, and it shows a negative differential resistance characteristic. That's very interesting, which have a typical device application. This work has just come in the last week or so. So if anyone is interested, can go through this thing. And for the kind of typical various carbon-based material, we have written a topical review article, which was there in the last year. So here you can see some of these interesting material where very few work has been published, and we have indicated that which one of them will be the future giants in this particular era. And you can choose your problem and do the calculation, check with some other calculations techniques. So I hope you will enjoy these review articles. And lastly, but not the least, this is another real space distribution technique where we have given the details how to calculate it for a two kinds of thing like decorated lattice and our proposed 2D material. So this also will be useful to you to start the calculations. So in conclusions, we have shown some calculations via the tight bending, and there are many applications of Dirac material. For example, it could be transparent to light for a given frequency. If a polarization dependent intensity can be controlled, the material would be opaque to the same light when it falls from other different directions. And this transparent conducting film, that's very important touch screen which is used in mobiles and other things. FET, the field effected transistor amplifier, has been obtained from this graphene thing. So there are many more workers going on, because I told you there are many attributes, many faces of these 2D materials are coming up in near future, like quantum spin Hall effect, and the topological aspect, that oil metals and other things. There are many more, and their thermoelectric properties, which are very important. Also from the basic aspect, like this robustness, like you apply some strain, that strain also will not change the position of the Dirac point. So you have to see or go through that why does it happen for that particular material. It happens that after 15% strain or the 17% strain, the material actually goes from a semi-metal to semiconductor. That kind of transition, the band gap could be either direct band gap or indirect band gap. So all these kind of simple problem related to the electronic band structure can be tackled with this thing. Even those structures which have a buckled one, this electric field also can control the electronic band structure. And in that case, it is judicious to again go from the tight bending calculation, apart from the DFT technique, to identify how the band gap depends upon the magnitude of electric field. That's a very interesting thing, and there are few works which have been done on that area, but there are some controversial issues with that thing. So with this thing, I must will conclude. So here are some few references based on this particular thing, and also there is an interesting book which we have written, one of my postdoc student who is now a faculty member in Vidyasagar College. So this can be also looked for. And and here are the people who are at present working with me, and some of them are submitting the thesis. So, and Susmita is also in IIT Madras as a postdoctoral fellow. He had joined last week, and Supro will go also to Jane CSR within a few days, and he has also submitted things. He has proposed many interesting 2D materials, and the others are doing work for a couple of years from now. They will also be able to contribute significantly to this 2D material. And with this thing, I conclude, and I thank you for your kind attentions. And I'll be happy if some clarifications and questions are asked. Thank you again.
So thank you, Professor Jana, for your nice talk and very informative one. Now we'll proceed to the audience if they have some queries and questions.
Okay. So I am within time, right? So
yes, sir. Yes, sir.
Okay.
Absolutely.
Okay.
Absolutely.
So that's I try to
exactly. It is 50 minutes. Exactly.
Yeah, very in time.
Yes. Right.
So any queries?
Sir, can I ask one question?
Sure. Please.
Okay. Sir, in one of your slide, you have talked about a relaxed structure. So can you explain it a little bit?
Relaxed structure means this is the optimized structure. So in the DFT theory, what is done is that it is a self-consistent density function theory, where you start with a structure, so you come to a optimized value of the lattice constant with the appropriate symmetry. It is a total energy minimization calculation. Okay. So we have written down the equation of state, and it has a global unique minima. So once you reach the global unique minima, we call it a relaxed structure. Okay, is that clear?
Okay, sir, I understand.
Yes, it's the global optimized structure, because that can be worked on. And the point is that in the DFT, this is the interesting aspect, that once you have reached this global unique minima, that is the optimized structure, you can do all sorts of calculation with this optimized structure. You do not have to do for, let's say, you would like to do optical properties, you would like to do the Raman effect, you would like to do the other magnetic properties. All these things can be done with that optimized structure. You do not have to do every time. That's the beauty of this thing. Okay.
Professor, I have one question.
Sure. Okay, please.
Really, very nice informative. You have just spoken about a Dirac material, which includes the graphene electronic structure even.
Right.
Then also you have talked about the two-dimensional van der Waals material. And not only that also you have mentioned a new kind, that is fast graphene also. So all are very nicely described to us. But one thing I want to know, that generally, if used VASP, it used generally pseudo potential actually.
Right.
So if using pseudo potential, is there a risk for some underestimation in the calculation?
Yes, you are rightly asked. So actually, I should have told that thing. This estimation of band gap is a serious issue in this DFT, because DFT, this cone sum equation does not give you the real total energy. There is this interaction and exchange interaction. And by the way, I have shown most of the materials not having this band gap. These are all Dirac material. But I agree that when you have a semiconductor, we have to test that band gap by various other exchange correlation. For example, we start with GGA first. That gives at least first rough and idea. Then we use age AC. Then you use GGA plus U, because you have a D band or F cell that atomic configurations, you have to use the Hubbard U metal. So by trial and error method, we propose that thing. But the most importantly is that unless we have no experimental observation, this is very difficult for us to compare. But we tried by all possible with the sophisticated exchange correlation function, what could be the possibility of this thing. And there are nowadays, I can tell you some further techniques where you can change it. I can tell one example that we know that silicon, the bulk silicon, this has a band gap of 1.21. So if you run any software program, you will never get this 1.21, either 0.78 or 0.68 or 0.98.
Yeah.
Now, so this is very amazing because this is the most important semiconductor which has been used in all the devices. But we do not know how to calculate theoretically these things. There are some techniques, and we have been able to, we have done some calculations which have been published in Carbon Journal with the collaborators abroad. We have solved this thing. There is some other Vanderbilt corrections with that thing.
Okay.
So that has been done. That's a very tough problem. And we were surprised that it has not been done earlier. So people have tried, because that's a problem with this DFT. I can tell you that we cannot tell explicitly this band gap for all the materials. Okay, thank you for asking this question.
Sir,
I have a
another
question.
point. I have seen you have shown two just direct points, both in RSDM and also DFT. Is it due to two spin degenerated direct cones?
Not spin degenerated, because spin has a different meaning. Pseudo spin has a different meaning. This is completely spin not taken into account here. This is the two bands, two pi bands cross each other. That I should say. Okay.
Okay.
Sir, I have a question.
Sure.
Thank you for, first of all, thank you for this nice talk. So the 2D materials which you have shown,
Yes.
do they possess any topological phases or something like that?
Only this PRB paper, they have these jack phases. You know that one, I think.
Oh, okay. The last one, I think.
Yes. So the other thing does not have. Okay.
I think that is because the whatever with the band gap that is opening in the middle of the below ozone or something like that.
Exactly.
But,
that is not occurring exactly at the Dirac point. Yes.
Yeah. Because for any topological phases to occur, the band gap should open at the boundary of the below ozone.
Exactly. So that's a very good observation. Absolutely correct.
Thank you, sir.
Okay, thank you.
Sorry. Yes, sir. So if there is no further question, so or if there is some question, I can also forward this question to Professor Jana.
I can take this thing and you can send me email. I can also answer.
So again, thank you very much, sir, for your very nice presentation. It is always very much interesting that I have found that either I am listening from you, either it is magnetism or it is superconductivity or it is tight bending model. I always found that it is very interesting, and I hope that in near future also we can also invite you. We can also.
Yes. Okay.
So thank you very much, sir.
Thank you.
Thank you.
Thank you, sir. Very much. Thank you.
Thank you.
Thank you very much.
Okay, thank you.
Now I think we have reached to end of our sessions. It's the last session that we'll start now.
So can we start now the final session of this today's seminar?
Yeah. Just a second. I'm starting the recording. Thank you so much, Sharupta and Bima sir, chairing the session so nicely. So now we have reached to our end session of YPM 2023. This is the fourth session. This chair will be chaired by Dr. Saurabh Kumar Niyogi, and it will be co-chaired by Dr. Tamal Kumar Mukherjee. So there, Saurabh Kumar Niyogi already, I think I have introduced him. No need to introduce again, I think. And Dr. Tamal Kumar Mukherjee was also here at the morning session. He is Associate Professor of Department of Physics. So over to you, Swarupta. Please start our last session of YPM 2023.
Okay, thank you, Papia. Thank you, Tamal sir. So let us start the session. The first speaker of this session is Dr. Karthik Malik from Vidyasagar Metropolitan College, Kolkata. Hello.
Hello.
Sir.
Yeah, I'm listening.
Yes. So please start your presentation. And so Dr. Karthik Malik will talk about analytical model to estimate the effect of periodic heat source and external load on the thermoelectric power generation. So, Dr. Malik, please start your presentation.
Okay, thank you. First of all, I want to thank organizer for giving me this opportunity. I want to discuss on the analytical model to estimate effect of periodic heat source and external load on thermoelectric power generation. We know that most of the heat source during the conversion of primary heat to our favorable heat, favorable energy, that is electricity, most of the heat is wasted, and almost 66% energy is lost as a heat. Only 34% are used. And here, in this case, thermoelectric device or thermoelectric generator may take part a crucial role. They can recycle heat to electrical energy. First of all, what is a thermoelectric device? Thermoelectric device or thermoelectric generator which convert heat energy into electrical energy or vice versa. And here mainly two basic principles is needed. That is, one is Seebeck effect, another is Peltier effect. Thermoelectric device is made of by two type of material. One is P-type material and it is N-type material. Both are thermoelectric material. And two material are connected electrically in series and thermally in parallel. And in this case, efficiency of the device, that the maximum efficiency of thermoelectric generator may consist of two type of material. One is P-type material and another is N-type material. Hence, the expression of the efficiency would be eta max is equal to TH minus TC by TH into square root of 1 plus ZD into TM minus 1 divided by 1 plus ZD into TM plus TH by TC. Here, ZD refers the device figure of merit. First of all, there are two kinds of device figure of merit. We may designate it. One is the materials figure of merit, that is S square sigma by kappa into T. But in case of device, as there are two type of material, N-type material and P-type material, so the ZT will be something different. Here TH and TC are hot temperature, and hot temperature, and TC is the cold temperature, and TM is the average of these two temperature. And ZT is defined as SP plus SN whole square divided by square root of kappa n into rho n plus kappa p into rho p whole square, where S signifies the Seebeck coefficient, and P and N correspondingly signifies the P-type and N-type material. And kappa is the thermal conductivity, and rho is the electrical resistivity. But here it should be keep it in mind that this formula may only give the efficiency when the variation of the thermoelectric parameter or the transport properties is very less with respect to temperature within the operation temperature. ZT temperature may be in the temperature independent over the operating temperature, but most thermoelectric devices have strongly temperature-dependent Seebeck coefficient, electrical resistivity, and thermal conductivity. Because the thermoelectric material we used, they are strongly temperature-dependent. This conventional model is not reliable on prediction for practical conversion efficiency of a module which is operating in a long temperature difference, where the temperature difference between the hot end and cold end is very big. In this case, we have to calculate in different way. The cumulative temperature dependence effect on the efficiency calculation. First of all, as there is a hot temperature and another is a cold temperature, then heat will be go into the device through the hot temperature, and it will be leaving through the cold temperature. And heat through the hot temperature will be there will be term that is a Fourier heat flow term in the p-type and n-type material, and there will be Peltier terms, and another will be the loss due to the Joule effect. Here, this is the Fourier heat flow within the p-type leg, and this is the Fourier heat flow in the n-type leg, and this is the Peltier term for the p-type leg, and this is the Peltier term for n-type leg, and this is the Joule heat flow. And similar way, this is the term for the cold side, and these are the Fourier heat flow term, and these are the Peltier heat flow term, and this is the Joule effect loss. And according to the thermodynamic law, we know that output power would be QH minus QC, and here we can see that it is a current, that is current flowing through the device, I into that is the hot temperature into Seebeck voltage minus for the p-type material, and this is the hot temperature, and for the Seebeck voltage for the n-type material. And correspondingly, this is for the cold type, cold end, and this is the Fourier heat flow, Joule effect. Now, efficiency will be simply P output by QH, that is the heat entered into the device, and here VOC square is the open circuit voltage due to the two thermoelectric materials, and RL is the external load connected with the device, and here is another term is there, that is M. M is nothing but the ratio of external load and the total internal resistance of the p-type and n-type material. And VOC is the difference of Seebeck voltage for the p-type and n-type. Here there is an integration because there is a temperature gradient within the p-type leg and the n-type leg. And from here we can calculate the maximum efficiency for a definite M, that is the optimum temperature M. In case of ordinary device, we know that in case of ordinary device, we know that the external load and the internal load is same, then the output power will be maximum. But here, in this case, for thermoelectric device, it is something different, that is M optimal, and it is related with the ZD engineering. What is ZD engineering? ZD engineering is nothing but this term, where this is the Seebeck voltage for the p-type leg and Seebeck voltage for the n-type leg, the whole square, and divided by square root of this integration of Kph and integration of rho p, and plus integration over square root of integration over Kn and square root of integration over rho n. Now, here we can remember that we first here we have defined that the ZD. In this case of ZD, that is for the device figure of merit, there was no integration term, because in this case, in this formula, all the parameters are considered the temperature independent. But here, as we are considering the temperature dependent, so here the temperature dependent value is arised. However, in order to get the reliability or determine the validity of our developed model, we have considered two thermoelectric material. One is P-type material, another is N-type material. One is Bi 0.5 Sg 1.5 T3, another is N-type material, that is Bi2 T3. And it is seen that the eta max is observed at around 400 Kelvin, and it is around 5% efficiency is seen. And the corresponding ZD engineering is obtained 0.2 is in the same temperature around 400 Kelvin. Here temperature difference is 50 Kelvin to 550 Kelvin, 60 Kelvin to 550 Kelvin. That is hot temperature is 550 Kelvin and cold temperature is 60 Kelvin. And it is seen that for ZT engineering 0.2 and the optimum value of M, that is 0.974, the maximum efficiency is 5%. Here it should be remembered that here there are another two terms, that is alpha term. Here alpha is multiplied by square root of 1 plus ZD engineering into this term. Here alpha is equal to delta T into SP of T minus Sn of T divided by integration over SP and minus integration over Sn. Here this term actually related with Thomson coefficient. We have not considered primarily the Thomson effect, but during the calculation Thomson effect arises because due to the temperature variation of the Seebeck coefficient. So in case of thermoelectric device, whenever we will try to calculate thermoelectric efficiency of a device for the material, we have to consider the Thomson term. And for considering Thomson, in case of considering Thomson term, the M optimum value will be changed. The magnitude of alpha, that is which is related with the Thomson term, if we vary the magnitude of alpha, then the ZT engineering is varies in this way. Whenever alpha is increases, the efficiency ZT engineering is decreased. That means also efficiency will be decreased. For the 0.2 alpha is equal to 0.2, the efficiency is the maximum. It actually smaller value of alpha indicates the lesser effect of Thomson heat comes into the smaller error or effect in the efficiency calculation. If alpha is low, then the Thomson effect in the efficiency calculation will be less. However, in general, in reality, there is no fixed temperature. Temperature actually varies in the temperature sources. So in order to get the flavor of this one, we have considered that hot temperature varies periodically, and as a result, the P output power also varies. And here in this case, for each delta T, we have here is the external load RL, and correspondingly output maximum power is observed. For suppose for the 350 Kelvin delta T, we have varied the RL from 0 to 10, and correspondingly output power maximum observed is around 0.345. In this way, we also get the periodic variation of output power. However, actually, in case of device, we need to know the average output power. Whenever we will use a device, we always want to know what is the average output power. So we have calculated also the average output power in case of periodic temperature variation, and it is observed that the average output power is maximum for the RL around 0.4. And after that, our power is drastically decreased. So whenever we will use a thermoelectric device, we also have to cautious about the external load, and it is related also the Thomson effect, and also the internal resistance, internal variation of the internal resistance of the P-type and N-type material. Now in this the conclusion, I can say that analytical calculation are performed using temperature dependent parameters. Primarily, there was no theory or model considering the temperature dependent variation. Here we have exclusively shown the each effect of each and every parameter which are dependent on temperature, and it is related with the efficiency, final efficiency of the device. And also due to this temperature variation, another term comes, that is the alpha, which is related with the Thomson effect. So Thomson effect also, Thomson coefficient or Thomson effect also affect the efficiency of the thermoelectric device. Also M optimal. What is M optimal? M optimal is nothing but the ratio between the internal resistance of the device and the external load divided and the internal resistance of the device. And in case of in general electrical device, we know that whenever the resistance between the input and output, that the device and the external load is equal, then the efficiency is maximum. But in here in the thermoelectric device, it is something different, and it is related with the ZD engineering, not the ZD. That is ZD it is related with the ZD engineering, and efficiency formula is also calculated. Thomson effect is included in the efficiency calculation through the temperature variation of rho, S, and kappa. Effect of periodic temperature variation is numerically estimated considering two well-known thermoelectric material. One is Bi2T3 and another is mixed crystal, using our developed analytical theory. These are the references. Thank you for your listeners.
Thank you very much, sir. So now the session is open for discussion. We can take only 1 or 2 questions because we are a little bit running short of time. So I would like the participants, if there is any question, they can also write it in the chat box, or they can ask directly because speaker is already present.
I can't see any question on the chat box. So
okay, so
also no hands.
So okay, so
okay.
Can I go for the next talk then, Tamal sir?
Yeah, let us thank the speaker again. And,
yes.
Yeah,
thank you, sir. Thank you, Karthik Malik.
Thank you
For your very nice presentation. We hope there will be a lot of interaction in future, and I hope that you will come up with very nice publication with this work. Thank you.
Thank you very much.
Okay, so may I now request Dr. Arindam Basu from SRM University, Andhra Pradesh, to please present his work. Hello.
Yes, sir. I am here. Yes.
Okay. So Dr. Arindam Basu will talk.
Sir, I'm not doctor yet.
Okay. Okay. So Mr. Basu will talk on a MeV scale boosted dark matter through Higgs portal interactions.
Yes.
Okay.
Yes.
So
Let
now,
me share my screen.
Please present your lecture.
Yes, sir. Is it visible?
Yes, it is visible.
Good afternoon, all. My name is Arindam Basu. Today's my presented topic is MEV scale boosted dark matter through Higgs portal interaction. To start with the dark matter, let us first know why there is no dark matter in standard model theory. So standard model theory is a very huge successful theory. It has
Hello. Mr. Basu.
time.
Yes. Now you are.
And then the fundamental forces are the strong force, electromagnetic force, and weak force. Unfortunately, there is no place of gravity in standard model theory, and this standard model theory contains 4.6% of the total energy budget of the universe. In this pie chart, we can see that atoms, 4.6% of the total energy budget of the universe. That is our visible universe. That is made up by the standard model particle content actually, and then there is 24% dark matter and 71.4% dark energy. This dark basically means that unknown matter and unknown energy. This doesn't mean that there is something huge condensed black kind of object there. That is not true. The dark basically belongs to means that unknown. Okay, this diagram we can see y-axis is the rotational velocity and x-axis is the distance from the galactic center. So if a star start its journey from the center of a galaxy towards the end of the galaxy, then the expected graph of the rotation of the star from the calculation of basic Newtonian mechanics can be this white dotted plot. But the observed data shows something else, where the velocity is actually becomes a constant or increasing nature after the end of the galaxy. So we can motivate ourselves by saying that there is a huge unseen matter in the vicinity of the end of the galaxy. And here in this plot we can clearly see the difference between the dark matter and dark energy. So dark matter and dark energy plays exactly opposite role to each other, where dark matter plays the role of gravitational pull effect on the galactic objects, and therefore and then their dark energy plays the role of extend the universe, stretching the universe. And due to the higher percentage of dark energy, so dark energy plays the upper hand, and the universe is keep on expanding. So let us say that we have motivated ourselves pretty well through a small slide, previous slide about the dark matter. But how to detect the dark matter? We have to detect the dark matter, right? So here is a toy model where A and A bar is the dark sector particle and B bar is a visible sector particle. So and this black patch is a unknown kind of interaction between this dark sector particle and visible sector particle. There are various detection procedure in the toy model also, where indirect detection shows that two dark sector particle can interact with unknown kind of interaction and unknown kind of interaction and give rise to visible sector particle. And detecting this visible sector particle, we can trace back to the dark sector particle. There is also direct detection method where one dark sector particle and one visible sector particle can interact and give another kind of dark sector particle and another kind of visible sector particle. There is also collider detection procedure where the LHC people, means the Large Hadron Collider experiment people in Sweden, they actually collide two visible sector particle, let's say proton, and they try to give rise a dark sector particle. So let's proceed with the Higgs portal model, where Higgs play the role of a mediator between a dark sector particle and a visible sector particle. Higgs has this peculiar behavior where Higgs can both couple with the dark sector particle and visible sector, both couple with dark sector particle and visible sector particle. So Higgs has coupling constant with the dark sector particle. This vertex has coupling constant, this lambda, and where A is the dark sector particle and phi 1 is a doublet, where one component of the doublet is a Higgs. And Higgs has standard coupling constant with the visible sector particle. That is our standard model particle through our standard model Lagrangian, based on the various symmetries in standard model theory. Okay, let's proceeding further. We can see this where phi 3 is a dark sector particle in our paper, and phi 3 is annihilating to standard model particles, all those fermions in standard model particle, W plus minus bosons, Z bosons, Higgs bosons also. So one kind of particle is annihilating to another kind of particles, right? So the number density of the first kind of particle, or we can say dark sector particle, can should decrease, right? So dark sector particle is basically annihilating to standard model particle. So the number density of dark sector particles should decrease. But there is a catch. The universe is also expanding, right? So that will play a role. that we can see in a little bit in a bit. In this graph, we can see the y-axis is the basically number density, n is the number density, and s is a dimensionless coefficient, and y is a coefficient for the betterment of our calculation, and x-axis is basically decreasing with temperature or increasing with time. And in the first patch, we can see that the number densities keep on decreasing, right? Because the interaction rate is basically higher than the expansion rate of the universe, and therefore the dark matter can annihilate to standard model particle and interact to standard model particle and annihilate to the standard model particle. So the number density of dark matter particle is decreasing, but after a certain point the number density become constant. For this blue dot, it's about 10 to the power minus 8 constant. So what is happening there? So after a certain point, as the universe is expanding, so the expansion rate of the universe is becomes larger than the interaction rate. So the interaction becomes stopped and the annihilation becomes stopped, and the density of the remaining dark matter is termed as relic density. That is the leftover dark matter density. In this slide, I have shown a detailed calculation, a small section of detailed calculation from our paper, where the Feynman diagram has this cross section for a phi 3 or a dark sector particle annihilating two fermions, standard model fermions. But what does this cross section means? Cross section in particle physics language is basically the probability that two particles will collide and react in a certain way. And then we have this expression for thermally averaged cross section. But why do we need thermally averaged cross section? Because with time with time the temperature of our universe is decreasing and the universe is expanding. So in this regard, we have to consider the thermal history of the particles involved in the interactions. We have to consider how they evolve with temperature, with the as the temperature of the universe is keep on decreasing with time. So that's why we have to take this thermal average cross section of this cross section for this annihilation diagram. In this slide, we have left equation is the Boltzmann equation, where these I'm not going into details of this Boltzmann equation. Just want to show this first component of the Boltzmann equation is our thermal averaged cross section, and we are getting this plot where the y-axis is number density again and x-axis is decreasing with temperature or increasing with time. And here the number density is decreasing for the first patch, and for the second patch it is constant. So we can predict the relic density from this constant portion. But in the next equation we have directly the relic density calculation. And from calculating this relic density, we are having this blue diagram, and this red diagram is basically experimental constant, shows equal a y-axis, a red line cutting the y-axis at 0.12. So to be a potential dark matter candidate, one has to satisfy the relic density equals to 0.12, and I am having the relic density 0.12 at dark matter with mass 1 GeV. In this slide, I have shown a boosting mechanism for the dark matter. So C is a dominant kind of dark matter with higher mass, and A is a subdominant dark matter with very lower mass. So the process of generation of A through C will energize A more. That is, A will become boosted, and then the boosted A will annihilate to the visible sector particle. So C will boosted up the subdominant dark matter candidate A, and therefore the detection of the boosted dark matter, that is A is very energetic, so we can call it boosted. And the detection of boosted dark matter A through annihilation of standard model particles, that is B, becomes easy. So this is our total dark sector particle, dominant and subdominant, and this is my visible sector particle. So this is the total boosting mechanism. And for this toy model, I have exact calculation in our paper. I'm not going into the detail, that will be complete jargon for the most of the audience. And just want to say that this Chi1 and Chi1 are the dominant dark matter in our paper, and it has a very large mass than compared to this Phi 3. Phi 3 is a subdominant dark matter. So this generation process will boost up this Phi 3. This is the cross section for this diagram, and this is the coupled Boltzmann equation. This again, I'm not going to the detail why coupled, why not only single Boltzmann equation. Just want to say that this coupled Boltzmann equation will give me this kind of plot where the boosting mechanism also included. So this Chi1 to Phi 3 is basically boosting mechanism. It will evolve in the coupled Boltzmann equation. So this term is also here. So that's why I am calling this two term as coupled Boltzmann equation. These two differential equation are coupled with each other basically. So I am having this plot, and not going further, I want to conclude here my talk. So in conclusion, standard model is hugely successful theory, but there is no dark matter due to the fact that there is no gravitational role in the dark in the standard model theory. And then the astrophysical observations and energy budget of the universe produce a motivation of dark matter, and we have see that the dark matter and dark energy is pretty different in the aspect of their role in the universe, and the detection procedure of dark matter is well described through Higgs portal toy model. And the relic density is the final thing, ultimate thing to look for, and it should satisfy the experimental constants. And finally, for the boosting mechanism, I just want to say that boosting mechanism is needed for a low mass dark matter to satisfy a potential dark matter candidate. Finally, at the end, I want to thank my supervisor, Dr. Amit Chakraborty, my collaborator, Dr. Soumya Sadhuka, and Dr. Nilanjana Kumar. Thank you all.
So now this session is open for some discussion or questions, but we can take only one or two questions.
Yes, but can't see any message or any questions in the chat box.
Okay,
So,
yes.
so
So can we proceed to the next talk now?
yes, sir. Let us thank the speaker again.
Let us thank the speaker for his nice presentation, and I hope that you will get good publication out of this work. So let me now request Sricheta Chaudhuri from SRM University, Andhra Pradesh,
Yes,
please present his lecture. And she will talk on probes of exotic top decays in hadronic collisions. Hello?
yes, sir.
Okay.
Can you hear me?
Yes, yes. Please present your lecture.
Can you see my screen?
Yes, it is visible.
So, good afternoon, everyone. I'm Sricheta Chaudhuri. I'm a PhD student at SRM University, AP. Today, I'm going to talk about probes of exotic top decays in hadronic collision. Now, before going into the details of my work, I want to talk about the standard model of particle physics for a little bit. Now, standard model of particle physics have two main genre of particle. One is a fermion and other one is a boson. Fermions can further be subdivided into leptons and quarks, and bosons can be subdivided into vector bosons and scalar bosons. Now, we can also see that the fermions have three generations of particle. Among that, top quark lies in the up-type third generation particle. Now, the up-type quark has the property of that it has a charge of 2/3, and the down-type quark has a property that it has a charge of -1/3. Now, knowing a little bit more about the top quark, as a fermion, it has a spin half, and it has a charge of 2/3, as it is a up-type quark. Now, it is a pictorial description of the mass top quark have, that we can see that it is the most heaviest particle in the standard model, and it has a mass of 172 GeV. Because of this massiveness, it doesn't get much time to form any bound state with other quarks. That is, it doesn't get much time to get hadronized. So it decays before it get hadronized, and that's why top core can be studied directly. So how it decays and how this what is the possibility of decay to other kind of core is can we get from the CK matrix. CK matrix is the Kabayashi Mascov matrix, which gives us that what is the probability of the decay from another quark to other quark. Now here we can see that it is a matrix representation of the probability, which is showing how up type quark is decayed to a down type quark. And from this matrix we can see that top quark has the highest probability to decay to a bottom type quark. It is almost 100%. Now, this is a pictorial representation where we can see that two proton in a proton-proton collision, top anti-top pair is generated, and then that top is further decayed to bottom and W boson, and W boson can have further decay procedures. But whatever we have discussed here, we have discussed that up-type quark, that is a 2/3 charge particle, is decaying to a -1/3, that is a down-type quark. So it is so through decay, a quark is changing its flavor as well as its charge. So this kind of decay is called a flavor-changing charge current decay. Now, what if a up-type quark decays to any of the up-type quark? Now, what will happen then? Then it will definitely change its flavor, but the charge will not change. So those kind of decay is called the flavor changing neutral current decay, or the FCNC decay. Now, for FCNC decay of top quark, it can decay to either C or U quark. But in standard model, this decay have a very small branching ratio. That is, it is almost of the order of 10 to the power -15. But there are other models which is beyond standard model, through which this branching ratio can be increased up to 10 to the power -4 orders of magnitude. So if you probe into those kind of scenario, we can that can lead us to new physics. Now, to study that, we studied two kind of process. One is what we wanted, that top quark is decayed to a charm quark and a Higgs boson. And other one is the normal standard model decay, that is a top going to a bottom quark and a W boson. Now on, I will call this one as signal and this one as background. So for signal, if we see at the top decay, the top is decaying to a charm quark and a Higgs boson, and Higgs is further decayed to bottom type quark, that is a B and a B bar. And here the top quark is decaying to a bottom quark and a W plus boson, and that W plus boson is further decayed to a charm quark and a strange type quark. So we can see that in final decay product, there is 3 quark in the top decay in both the process. So if there is 3 decay, as I also told earlier, that quarks in general doesn't leave like a single quark. It always form bound state with other quarks, and those fragmentized or bound states of hadronized particle forms collimated spray, which is called a jet. Now, as we have seen that background process, it has one B quark and one W boson, and that W boson also decayed to 2 kind of quark. So those can generate these 3 kind of jets after that. So if our if the PT of the top quark is very low, then this can be separable. As we have seen in this picture, that this is well separated. But if the PT is very high of the top quark, then these decay products can be highly collimated. So here, what we took is we took a radius of 1 of the cone to understand if it can accumulate all the final products in it. So for that, first we what we did is first we did the jet multiplicity plot, and we can clearly see that it has a 1 jet multiplicity for most of the events. For signal and for background, both the process, it has a 1 jet event. So further, to check if it is a top jet, that is top mediated fat jet or not, we did that transverse momentum plot of jet. Now we can see here clearly it is peaking at around 350 GeV, which now we took for our simulation purpose that 350 GeV, we set the cut for our minimum transverse momentum of a top core, which is reflected in this figure also, that jet is also having maximum event with 350 GeV PT cut. And again, to get more confirmation, we did the mass plot, and the mass of the jet is peaking around 170 GeV. So 170 GeV is the mass of the top core. So we can confirm from here that what jet it's produced, it is a top mediated jet. Now further, as we had 3 final cohorts, so there should be 3 subjects within that fat top jet. So we can see that for signal and background, both the process, the subject multiplicity is peaking at 3. And as there was 2 B-type quark in the signal process, we can see that BZ multiplicity is peaking at 2, where for background it is peaking at 1. For CZ multiplicity, as both the events have 1 CZ, 1 C quark, so CZ is having 1 CZ even in both the process. Now, which jets are not tagged as B or C, we tag them as a light jet. Now, for light jet multiplicity, what we see that for signal process, it is peaking at 0, which is obvious that because our final state particle in signal have 2 B-type quark and 1 C-type quark. So 3 of them, if are tagged, then there is no such light jet. So for signal process, we can see that light jet is peaking at 0. And for background process, we can see it is peaking at 1, because there was another strange type of quark which can also form a jet, which will then tag as a light jet. So for background, it is peaking at 1. And we can see that there are other contributions too, that is 1 light jet for signal, 2 light jet for signal. There are few such events also there. So this is reflecting again to the subject multiplicity, as there was a small contribution to 4 and 5 subjects. Now we have also explored certain kinematic variables, that is the transverse momentum of BZ and CZ and mass of BZ and CZ. Here we can see that transverse momentum of BZ and CZ is having well separation between signal and background. Similarly, for mass also, we can see that they can be well separated, well understood. Especially for transverse momentum of CZ, we can see that if we put a cut on this 600 GeV, then there is no signal event left after this. There is only background event. So signal events mostly squeezed within this 600 GeV part. So signal and background is well separated in this kinematics variable for signal and background process. We also explored this energy fraction and mass fraction. Now I want to tell a little bit about the energy fraction. Energy fraction is basically we took how much energy a subject is taking from the fat jet, how much energy a subject contains of the energy of the total fat jet. Now we can see that energy of the B jet is taking almost more than 50% of the energy of the fat jet, whereas C jet for signal process is taking only 10% of energy of the fat jet. Now for mass fraction, we can see that the invariant mass of 2 subjects is taking almost 50% of the mass of the total fat jet, whereas the mass of the invariant mass of BB bar is taking only about 30% of energy, 30% of mass of the total fat jet. Now we explored several other variables too to classify or distinguish between the signal and the background processes. And for that, after that, we did a multivariate analysis. Now, for multivariate analysis, we used a machine learning technique. We took boosted decision tree as a classifier, and we can see, and here we have plotted receiver operating characteristic. In the x-axis, we have plotted the signal efficiency, and in the y-axis, we have plotted the background rejection. Now, we can see for 80% of the signal efficiency, we have only 10% of the background efficiency. 80%, almost 80 to 90% is rejected, background is rejected. So we can say that the signal and background can be well classified in this process. So that's all I want to conclude here by saying that we have focused on the flavor changing neutral current decay of top core. We have discussed about several variables to distinguish this process from the common standard model background. And we also did a multivariate analysis to find the efficiency of the signal over the background. So thank you.
Thank you very much. Thank you very much for your very nice presentation. Now the session is open for questions or comments, if any.
Yes, sir. There is one question from Jyotirmoy Kharat. So he's asking, hello, ma'am. Can you please explain what kind of test is done for the analysis of the jets?
What kind of test means?
I don't know. So Jyotirmoy, if you are there in the audience, please unmute yourself and ask the question yourself. Jyotirmoy, are you there? Jyotirmoy Kharat?
Jyotirmoy, are you present? Can you hear us, Jyotirmoy?
Yes, I don't have mic in my PC.
Oh.
Okay. Okay. Anyway, maybe I mean you can contact the speaker later on also. I mean, so yeah. So there is no other questions. I mean, in the chat box at least.
Okay.
Okay, thank you, sir. Thank you for giving me this opportunity to present here my work.
Okay, thank you. Thank you very much for your very nice presentation. Kamal sir, can we go to now?
Yes, sir. Yes, sir. Please.
So in this session, next speaker is Ms. Vishalika Sharma from Punjab University. Hello.
Good afternoon.
Hello, madam. Yes. So please present your lecture, and she will study on comprehensive study of old open clusters using multi-wavelength data in GA-IA areas. So I request, please start your presentation.
I hope my screen is visible, sir, and am I audible?
Yes, you are audible and we can see your screen.
Okay. Good afternoon, everyone. I'm Vishalika Sharma from Punjab University, and I'll be presenting the topic Comprehensive Study of Old Open Clusters, Berkeley 45 and Tombow 4, using multi-wavelength data in the Gaia era. I'd like to thank YPM 2023 organizers for giving me this opportunity to present my work and Adamas University. I'm very grateful to Dr. Ashish Raj and Dr. Devendra Bisht, who have guided me throughout this project and without whom this endeavor wouldn't be possible. I'd like to begin with the very basic of star clusters. These are essentially groups of stars which are gravitationally bound and are formed from the same molecular clouds. And these serve as excellent astronomical observatories for the same reason, because they have similar chemical compositions and similar ages. Now, these are of two types, open clusters and globular clusters. The number of stars in these clusters can vary from few tens to millions. Our focus of this study will be old open clusters with multi-wavelength data. These clusters also give us important insights towards the galaxy's structure and the evolution. For example, globular clusters, they are very old, and some of them age up to billions of years old. So they give us an estimate of the age of the galaxy itself. Here I've included an image of NGC 6380, which is a Hubble Space Telescope detected cluster. Moving on, a little bit about globular and open clusters. Globular clusters are much larger and they are much denser. In this image taken by the Hubble Space Telescope by NASA of NGC 1850, we can see that globular clusters generally have a spherical shape. They are more dense and they are more stable, and the stars in these clusters are relatively older in comparison to the open clusters, which are less dense. And here, as we can see in NGC 299, again, an image taken by the Hubble Space Telescope, it is irregular in shape. Here we can see a very spherical shape, and here it's an irregular shape, and there are less number of stars, which is also generally the case for other open clusters. In this present study, we have used two data sets, that is the Gaia early release data set and 2-mass data set. I'll be telling a little bit about both of these. Now, the Gaia early data contains very accurate proper motions, positions like right ascension declination, parallax data, and also G magnitudes and color indexes for about for more than 1.5 billion sources. Whereas the 2-mass data, which was released in 2003, is a point source catalog. It is in the near infrared light and offers us the JHK magnitudes. Now, we'll be using the 2-mass data for estimating the interstellar reddening, which will be discussed in the presentation ahead. Our aim in the study is to utilize these two data sets to determine the mean proper motions, mean parallax, the member stars in the clusters, the ages, reddening, and other dynamical properties, including the blue straggler stars. The sources for these data sets have been given down below from where we downloaded it. A little bit about the literature overview of Berkeley 45. I'll be quickly going through this. The galactic coordinates have been taken from the Web.data database. It is to be noted that Berkeley 45 is in a very crowded and a very rich galactic field in the Aquila constellation. There have only been 2 studies to the best of our knowledge, which is by first is by Subramaniam, who predicted a log age of 8.5 to 8.6 and reddening of 1.4 magnitude, whereas Tadros predicted log age of 8.77 with a reddening of 0.82. Also, a very interesting thing to note in this cluster is that it shows asterism, which we will be examining with Gaia 3 data as well. If it shows us asterism in this particular study as well, the references have been listed for both the papers. Tombow 4 is also a very rich cluster. There are only 2 studies existing for this cluster as well, with log age 8.6 to 8.7, magnitude 1.25, and in the other study, log age of 9 and reddening of 1.01 magnitude has been calculated. Both studies that exist for this cluster have used the CCD-BV optical data sets. Now, coming to the RE deck of Berkeley 45 and Tombow 4. In this previous slides that I mentioned, that Berkeley 45 is in a very crowded region, it is seen here clearly because the search radius for both these clusters has been taken as 10 arcminute, but it can be easily compared that the stars in this 10 arcminute region are so much more significant in number than the one present in Tombow 4. I have marked the red circle because this is where our cluster is present, and cluster center coordinates have also been estimated. In Tombow 4, we can easily see that there is a dense formation here. This is the cluster that we'll be analyzing. Moving on to the membership analysis. Whenever we are studying about open clusters, the very first step is to determine the cluster member stars. To do this, there are many methods like dbScan or GMM. Here we have used PyUpMask, which is built over the UpMask package written in our language, but we have used the Python version here. It takes into account the proper motion, parallax, and other coordinates, positional coordinates like RADEC to calculate the membership. This is the GMAG versus probability graph, and the cluster stars above 90% probability have been marked in red in both the cases. Now, when we downloaded the data set for 10 arcminute for Berkeley 45, we got a huge number of stars, that is 21,954 stars. After running the analysis and estimating the member stars, we got 699 stars above 90% probability for Berkeley 45 and 484 stars for Tombow 4. The reference for the algorithm that we used here, PyUpMask, is given right here. For estimating the mean parallax, which is the apparent displacement of any object in the sky, for Berkeley 45, we calculated it as 0.304 and Tombaugh for 0.47. We have used the G magnitude versus parallax graph, where solid dots represent the cluster members above 50% probability, and the empty dots are representing the field stars which are less than 50% probability. We have also used 0-point offset here of minus 0.029 mass. Moving on to the next slide, which is the PM RA versus counts and PM dec versus counts. This is the proper motion RA and proper motion declination. The mean values calculated have been mentioned here. Now, why do we calculate this? Because we want to know the change in the object's position in the east-west direction and the change in object's position in the north-south direction in the celestial sphere. So we calculate the PMRA, PM dec. Also, I have shown a vector point diagram right here for both the clusters, for Berkeley 45 and for Tombaugh 4. This vector point diagram is made with the help of PMRA versus PM dec. Many studies have also used this diagram to estimate membership by visual inspection, which is also a useful method, but this is showing the object's motion in the celestial sphere. Moving on to color magnitude diagram. Now, this is a very essential tool to analyze any open cluster, because this particular diagram is going to give us the evolutionary stages of the stars. We can locate the main sequence stars, the giant stars, the blue stragglers, the main sequence turnoff with this diagram. And it can be helpful in measuring the age, reddening, composition, and also studying the temperature and the spectral types. It is very much similar to the HR diagram. Just the difference is that the HR diagram shows us the spectral types of the stars. However, in this case, in Gaia ADR3 data, we are going to use G magnitudes and GBPRP, which is the color index. We'll be using a cutoff for G magnitude as 20. We can also use other photometric systems like UVV systems to plot the color magnitude diagrams. In this study, we have compared our CMDs with Canted-Gordon catalog from the 2020 paper, shown further. First, we'll look at the CMDs for Berkeley 45. Here we have constructed field star CMD, cluster star CMD, and all star CMD. In the very previous slides, I mentioned the interesting pattern which forms in Berkeley 45, which is also called as asterism. Now, it is to be noted that these stars are not gravitationally bound to the cluster, but we see a pattern here, which is not otherwise observed generally in the CMDs of open clusters. Also, it is to be noted that Berkeley 45 CMD does not offer us a very clean main sequence turnoff, which is right here. And it also is not giving us a very clean giant branch because of the asterism pattern. But in Tombaugh 4, we can see a clean giant branch here. We can also see the main sequence turnoff point clearly. There is some scatter, but it is not as significant as the asterism present in Berkeley 45. The comparison with Canted-Gordon catalog, the reference is given below. They used a G magnitude cutoff of 18. They used the Gaia DR2 dataset. In Berkeley 45 Canted-Gordon CMD, there again, the presence of asterism is confirmed, as we can see in this pattern here. And in Tombaugh 4, the scatter of the stars is much more than the one we obtained here for Gaia DR3 data. This shows that Gaia DR3 data is more clean and more precise because the amount of scatter has decreased significantly here in comparison to the DR2 data. To calculate the interstellar reddening, when we want to observe any celestial object in the sky in our line of sight, there is a lot of interstellar dust and gas present, and the light coming from that object is often scattered and absorbed. Thus, it causes reddening. To calculate this parameter, that is the EBV, we will be using the 2-mass data, which is the near infrared JHK's photometric data. We'll be plotting the JH versus JK color diagram, and we'll be fitting the solar metallicity ZAMs from Caldwell. We'll check that the ratio of EJH EJK as well, which is if it is in good agreement with the value given by Cardelli. in the reference number 2, which is 0.55. We'll also be obtaining the EJH and EJK values using these equations given by Firoshi and Munari in the reference number 3. The obtained values for intercellular reddening for Berkeley 45, here the dotted line is the Caldwell fit, the Zam's fit of solar metallicity. The EJH and EJK ratio for Berkeley 45 is 0.55 and for Tombaugh 4 is 0.59, which is in good agreement with the one obtained by Cardelli, which was 0.55, as I mentioned in the previous slide. For Berkeley 45, we have obtained a reddening of 0.80. In the previous, very previous slide, when in the literature review I mentioned, Tadros had obtained a value 0.82, and we have obtained a value very close to that with 2 months data. So it confirms that our results are consistent with the present literature. For Tombaugh 4 as well, we have obtained a reddening of 1.012, and in literature, in the CCD-BV survey of 42 clusters, the EPV was obtained as 1.01. Again, this confirms that our results are consistent with the literature. Coming on to the final parameter, which is isochrone fitting, and a really important parameter to determine the age of the cluster. This is a theoretical model which depicts the evolutionary stages of stars. So we have to select a particular log age and metal fraction of a concerned cluster, and then we have to fit it upon the observed CMDs. Here we have used parsec isochrones with the CMD tool, reference given right below. We will be also marking the blue straggler stars, the potential blue straggler stars, which are often formed near the main sequence turn-off point. Going to the final slide. For the cluster Berkeley 45, we have shown 3 isochrones of log age 8.9, 8.95, and 9. From visual inspection, we can see that the log age 9 isochrone seems to fit the main sequence turn-off, the giant branch, and the main sequence very well. Here, I have marked 4 blue straggler stars. Out of these 4, 1 blue straggler star is confirmed already with the RA of 289.771285 and declination of 15.707554 by Vikrant Jadhav and Annapurna Subramaniam. Out of these 4, 3 are not confirmed yet, but these are potential blue stragglers because the formation of blue stragglers is always near the main sequence turn-off, also present in the Tombaugh 4. These stars are generally more luminous and more blue than the normal stars, and they do not evolve to the giant branch, but they somewhere are formed near the MSTO. For the Tombaugh 4 cluster, we have estimated a log age of 9.2. Although the log age 9.15 and 9.25 isochrones are also given, but the log age 9.2 isochrone seems to fit the main sequence giant and the turn-off point really very well. This marks the end of the presentation, and our future works include some dynamical studies of the clusters like mass function, initial mass function estimation, and luminosity function. I hope I get the chance to present that in the later studies. Thank you so much for giving me the chance to present my work. Again, I'd like to thank the organizers and Dr. Ashish Raj, Dr. Devendra Bisht for guiding me throughout. Thank you so much.
Thank you, madam. Thank you for your very nice presentation.
Thank you, sir.
So now the session is open for 1 or 2 quick questions.
Yeah, Vasalika. Hello. Can you hear me?
Yes, sir.
Yeah. So, what do you mean by asterism? Actually, there is a sequence of open cluster, and in your CMD, there is another not very populated, but a poorly populated sequence, which is you are saying asterism. So, how
Yes,
you will differentiate that open clusters main sequence with this asterism? So, what properties are differ actually? Yeah.
So a very major point that differentiates the stars in asterism and the ones in main sequence is that the stars in asterism will not be gravitationally bound to the star cluster, and we can always check this by calculating the radial distances of those stars from the cluster center. So if we do that, we can confirm that those stars are actually not a part of the cluster, but just a pattern, not of the member stars.
Okay.
So Tamal sir, can I go to the next speaker now?
Yes, because I can't see any questions in the chat box. I can't
Okay.
see any. Yeah.
So let us thank the speaker once again for his nice presentation. And in this session, next speaker is Dr. Otonu Nondi from Acharya Prafulla Chandra College, West Bengal. Otonu, can you hear us?
Yes, am I audible?
Okay. Please present your lecture. Dr. Otonu Nondi will talk on general overview of flat band networks. Over to you, Dr. Otonu.
Am I audible?
Yes, you are audible.
Okay, so can you see my screen?
Yes, yes, your screen is also.
Okay. So good afternoon, everybody. So the title of my presentation is General Overview of Flatband Networks. So these are the plans of my talk. First, I will talk about some motivational background, and then the basic idea of flatband localization, and then some model systems, and then the result and analysis part, and then I will conclude my result. As we all know, that the single particle eigenstates always localize exponentially in disordered media, and which is the pioneering result of P.W. Anderson in the year of 1958. But unlike the case of Anderson localization, observation of flat band localization in several low dimensional networks has attracted the spotlight of fundamental research. And this journey started nearly 40 years ago from Sutherland. And this unconventional localization has generated significant attention because of its connection with the various novel physical phenomena, including fractional quantum Hall effect and flat band ferromagnetism. So motivation comes from this recent experiment, which I always prefer to show. This Shevabruto and his group members, they have shown the photonic localization, the flat band modes, and in the simulation process, they have used a femtosecond laser writing technique in the simulation process. And I'm not going into the experimental details. So this is basically the motivational aspect. So the obvious question comes, what is flat band localization? Flat band is basically the locus of zero mobility points in the momentum space. Basically, what happens for some particular energy eigenvalue, the non-zero wave function amplitudes are concentrated within a finite size cluster of atomic sites. And one such cluster is effectively decoupled or isolated from the other cluster of atomic sites by a special vertex where the amplitude of the wave function is 0. So the kinematics of the single particle eigenstate gets quenched for that particular eigenstate, and due to the extremely low group velocity of the associated wave packet, there is a momentum independent contribution in the band dispersion profile corresponding to that energy eigenvalue. So this is the essence of flat band localization, and the corresponding eigenstate is also named as compact localized eigenstate. So today's discussion is divided in four subcategories. First, I will talk about some periodic geometry, and then some fractal structures, and then some decorated lattices and some optical lattices also. So first, periodic geometry. The first example is square Kagome geometry. This is a quasi-one-dimensional network, and the system is picturized here. The schematic diagram is shown here, and that is described by the standard tight binding Hamiltonian shown here. And the first part, which is the epsilon, that is called the on-site potential of any particular atomic site, and T, which is the off-diagonal part of the Hamiltonian, that is the that carries the kinematic information of the Hamiltonian, that is called the hopping integral term. Also, in our analysis, we have used the discretized version of the Schrodinger equation, which is also known as difference equation. So with the help of real space decimation scheme, so one can transform the whole system into an effective two-arm ladder with the corresponding potentials. So the potential values are shown here. So epsilon tilde is the effective on-site potential. Gamma is the inter-arm, that is the hopping integral, which is marked by the green line. And tau is the intra-arm hopping integral, and xi is the second neighbor hopping integral. So here, for this effective network, one thing which we have to remember that this is just a mathematical construction, and we are nothing doing with the lattice, original lattice. That remains intact in our calculation. So for this effective ladder network, one can write down the difference equation in a compact matrix form, which is shown here. Here, this is the potential matrix, and this one is the hopping matrix. Here, the form of the potential matrix and the hopping matrices are such that they will commute with each other, and hence they can be simultaneously diagonalized. So one can go for a change of basis. So this is the new basis, and then in the new basis, one can write down the difference equation again. So these two equations now are linearly independent of each other. And now look at the second term, the second equation, second equation, the right hand part, the tau and xi, there is a hopping term tau minus xi. So if we go back to the previous slide, so the functional form of tau and xi are equal, exactly same. So basically the hopping integral part of the second equation is 0. So that gives some atomic like eigenstate, and the which is also named as compact localized eigenstate. And in the in terms of the band dispersion, that gives the flat band contribution. So this is the standard density of eigenstates plot and the transmission characteristics. And whatever I am saying in my previous slide, that for those eigenstate flat band states, the non-zero amplitudes are concentrated within a square, within a cluster of atomic size. Here the cluster is a square, and one such square is effectively decoupled by a special vertex, by this vertex, white vertex, but the amplitude of the wave function is 0. So this gives the essence of localization, flat band localization. So we have also calculated the band dispersion. The momentum independent flat line is prominently seen here. So this is the thing. And for those flat band eigenstates, non-resonant eigenstate, one should expect a spectral divergence due to the extremely low group velocity of the wave packet. And this is tested here. And this is because of this is basically the indicative signature of the zero mobility of the corresponding wave packet. Actually, what happens, the effective mass tensor becomes infinitely heavy for those particular eigenvalue. That means the particle cannot move. That means that is why the mobility becomes 0. That's basically the reason of this spectral divergence or singularity. Now we have incorporated a magnetic flux inside the square placket, So due to the basics of Aharonov-Bohm effect, as we all know from the basic quantum mechanics, the hopping integral takes a phase, which is the Pearl's phase, and due to that Pearl's phase, now if we calculate the flat band thing, the related thing, now the flat band is dependent on the magnetic flux. So here is the equation, energy eigenvalue equation. So here an interesting point is that since magnetic flux is an externally tunable parameter, so one can control the position of the flat band using the externally tunable external parameter, that is the magnetic flux. So these are the density of states plot for different flux values shown here. So this is the allowed enter eigenspectrum, where one can easily see that the E is equal to epsilon minus 2t cos theta. There is a flux dependent flat band state is present. So one can control, one can engineer the position of the flat band using the magnetic flux again. So the same analysis goes for the second example, which is the diamond dot periodic array. Here also the same thing, that is the one non-zero amplitude cluster is effectively decoupled from the other one by a special vertex where the amplitude of the wave function is 0. So here the flat band is at E is equal to 0, the central flat band, and this is a robust kind of flat band. That means whatever be the external perturbation, external magnetic flux, the flat band still retains in the spectrum. So this is the density of states plot for different flux values. So the central flat band retains whatever be the flux values. So this is the contour plot of group velocity of the wave packet. So red line indicates the zero group velocity, and the others are non-zero group velocity contours. So one can control the group velocity of the wave packet by suitably by using the magnetic flux, which is an externally tunable parameter. And also one can control the effective mass also, because all these things are related by the standard band theory stuffs. So one can control the effective mass. That means the effective mass means the curvature you can control. That means and that can be controlled using the magnetic flux. Next part discussion is for the fractal network. Fractals is a self-similar kind of network. So the first most prominent candidate of the fractal family is the Sierpinski cascade fractal. We have used the real space renormalization technique, and the right one is this is the part of an infinite network, and the right one is its renormalized version. Here, using the real space renormalization scheme, one can obtain a hierarchy of those flat band modes. There's a countably infinity number of sub flat band modes, and for those flat band modes, as beautiful staggering effect in the localization. That means the onset of localization may be delayed by a suitable choice of the energy of the electron. So that is a beautiful staggering effect can be seen here. So now the dispersion calculation part. So as we all know that fractal is no longer a translation in invariant network. So we have taken an indirect but effective procedure to calculate the dispersion here. Actually, we have taken a finite generation periodic array of finite generation fractal, and one can convert it into an effective linear chain by using the real space renormalization technique, and one can plot the band dispersion here. These are the plots. So these flat band modes are easily visible for any members of the Sierpinski cascade family. And the same analysis goes for the other one. That means this is the example of simplex fractal geometry. The same thing or same analysis goes here also. And this is the density of states and the amplitude distribution for E is equal to some epsilon minus 2t. And the density of states is calculated using the standard Green's function technique, as we all know. And these are the band dispersion relations. And the flux dependent flux contour flat band is also present here. This is the entire eigen spectrum, and then there's some decorated lattices. Here we have taken a periodic array of diamond. Am I visible? Am I audible?
Yes, you are audible. Yes.
Okay. Actually, there are some network issues, so I am repeatedly asking you.
Okay, you are audible.
Okay.
You are audible.
Okay. So here there is a periodic array of diamond. It's a simple diamond array, but each arm of the diamond is decorated by a quasi-periodic Fibonacci geometry. As you all know that for Fibonacci bond model, there are two types of bonds, long bond and short bonds, and there are two types of hopping parameter associated with those two bonds, respectively TL and TS. And for this kind of network, there is one thing is interesting, that there's a interesting spectral competition between the horizontal periodicity of the structure and the transverse aperiodicity in the structure. So it's a beautiful competition between spectral competition, I think. For this structure, we have also calculated the band dispersion relation. So this is the dispersion less contribution, and this is the momentum dependent dispersive part. So this is the mathematical details. I'm not going into that. So we have plotted the dispersion relation, and for the usual Fibonacci kind of thing, we all know that there is a 3 subband kind of the spectral nature is prominently seen here, and these are plotted for different flux values. And the last one is very interesting. There are a set of parallel lines, and that is obvious because for the last case, the flux value is the half flux quantum, and for that half flux quantum, what happens? The effective connectivity between the two axial points actually vanishes. So that is the essence of extreme localization of eigenstrokes. So that's why the particle completely loses its mobility, and then the momentum independent contribution comes into play. So now the optical analogy part. Here we have taken a Kagome network. This is the basic Kagome network, and a finite generation Sierpinski cascade fractal is embedded inside the skeleton of that particular network in appropriate fashion. And we can think of a waveguide, single channel waveguide, which is made in the form of the same kind of geometry. Okay, and these things can be transformed into an effective ladder by using the same real space decimation scheme. So why we can use the same analogy here? The reason is here. Actually, the wave propagation inside the core of the material of the waveguide is governed by this kind of standard second order homogeneous differential equation, which has the sinusoidal solution, something like this. So after imposing the flux conservation condition, this solution turns out to be like this. And this equation is very much similar to the difference equation, which is the discretized version of the Schrodinger equation, which we have used in the case of electronic case. So there's a one-to-one correspondence, one-to-one mapping. So one can cast the whole mathematical artifact here, and the same analysis goes here, and one can easily calculate these are the photonic dispersion relations in terms of the frequency of the incoming wave, and these are the photonic density of eigenmodes for different the upper one is the density of eigenmodes, optical modes when there is a first generation fractal is incorporated in the Kagome network, and second one is the second when there is a second generation fractal network. So these are the photonic dispersion relation, and as we see that with the increase in generation, several flat and dispersive bands will appear in the close vicinity of each other. So this dense packing therefore opens up a possibility of engineering the so-called slow light, because in terms of photonics, we can say that if the corresponding to that flat band modes, the correspondingly the velocity of the light waves becomes very low or extremely zero, or that's why I'm calling it a slow light. And there's a possibility of re-entrant mode crossover also, and thus the network this kind of model system can behave as a photonic switch which selectively goes off and on over arbitrarily small frequency intervals. So this is the again cluster like distribution, and one finite size atomic cluster is effectively decoupled from other cluster by some special vertex, and these are plotted for different frequencies. So now the conclusion part. We have discussed analytically exact scheme to discern the compact localized modes for different quantum dimensional systems, and flux dependent flatband modes may throw an achievable challenge to the experimentalists to test the analytical result with suitable fabrication mechanism definitely there. And the optical analog of the electronic case discusses the possibility of proposition of single channel waveguide network. And these are the acknowledgements. A very big thanks to the organizing committee, especially Sharupda, for giving me this opportunity to present my work in this platform. And a big thank you to my group members for their immense support, and Department of Physics, APC College, for providing me this proper research ambience. And before ending my presentation, this is a brief introduction of my research group. Professor Arunabh Chakraborty, my mentor, Dr. Biplab Pal, my senior member, Dr. Amrita Mukherjee, and some other collaborators, Professor Jana, he is also an invited speaker of this conference. Dr. Srikanto Shil from Vishwabharati, Orco, he is now at Bangalore, and some other project students who have worked with me over past 3 years. So this is a beautiful snapshot of my college, APC College, Acharya Prabhu Chandra College at New Barakpur. So finally, thank you for your kind attention.
Thank you very much, Atanu, for your very nice talk. So we can take now some questions from the audience.
There is no question in the chat box.
Okay. So I think there is no question, Thomas, sir, still now in the chat box also.
Yeah, so let us thank the speaker and move on to our next topic.
Okay. So let us thank the speaker once again for his very nice presentation, and we hope that in future also we will see more lectures from you, and also there is a lot of connections between your college and our universities. So let me now go to the next speaker in this session. Dr. Abhijit Sen from Shama Prasad College. Dr. Sen, are you present?
Hello, can you hear me?
Yes, yes. So Dr. Sen, his presentation is based on ab initio computation on X-ray spectroscopy. So Dr. Sen, please start your presentation.
Good afternoon, everybody. Thank you, the organizers, for giving me the opportunity to talk in front of you, and also rescheduling my talk from yesterday to today. Today, I will be talking on X-ray ionized spectroscopy from ab initio ionization potential computations. My name is Abhijit Sen. I'm assistant professor of physics in Shama Prasad College. The outline of my talk is as follows. First, I will briefly talk about the motivational part where I will explain some X-ray photoelectroscopic phenomena. Then I will give you some brief theoretical framework of our method, and then at last I will show you some results reproducing the experimental spectra with the theoretical computation. As you all know, X-ray photoelectron spectroscopy has gained tremendous popularity in the recent years due to the tremendous achievement in the synchrotron radiation in CERN and other places. There is also theoretical trends to reproduce the experimental X-ray photoelectron spectroscopy theoretically in the theoretical arena. So first, let me briefly explain the various terminology used in the X-ray photoelectron spectroscopy. When an electron from the 1s core hole is knocked out from the system, that is the ionization process, and that is called the X-ray photoelectron spectrum. When the electron is not out from the system but it remains in the system, then it is an excitation energy framework, and it is called X-ray absorption spectrum. Due to the knocking out of electron from different orbital like K cell, L cell, M cell, it is called K-edge X-ray absorption spectrum or L or M edge spectrum. In the figure you can see that in the left panel. In the right panel, we can see when an electron from the core hole is ionized, then an electron from the valence orbital try to fill this up, giving an extra photon, and that is called the X-ray emission spectrum. Whether the electron are coming from the 2p cell, it is called K alpha XCS spectrum. If it is coming from the 3p cell, then it is called the K beta spectrum. Traditionally, this X-ray emission spectrum is dealt with transition metal complex, where there is a ligand, metal and ligand bonding. So the transition density matrix is very important in this role, and it determines the selection rule of the X-ray emission spectrum. So the orbital of the metal also, as well as the ligand, contribute in the transition metal complexes X-ray emission spectrum. So in the molecular framework, this is done conventionally. This is done in the atomic physics field, but in the recent times, molecular computation is also done to reproduce the experimental spectrum. So in the molecular spectrum, we all know that the occupied orbitals are represented as doubly occupied molecular orbital or singly molecular orbital, and the virtual orbital are kept vacant. So an X-ray photoelectron spectrum introduces a state with a core hole state, and an X-ray emission spectrum you have to extract all the states and calculate the transition dipole moment between the core hole state with all the valence states. That will give you the X-ray emission spectrum. So this is basically our overall approach. If we go again into the transition metal complex, then you can see here that the representative figure depicts a 6s ground state where an electron from the core hole is ionized, and there are 5 upspin electron in the 3d orbital, giving a 6s ground state. If an electron from the 3p orbital, if an upspin electron from the 3p electron tries to fill this 1s hole, then it will give you a 7p to 7s transition in the XCS spectrum. Likewise, if an downspin electron from the upspin electron from the 3p orbital tries to fill the 1s core hole, then it will give you a 5s to 5p transition. The ratio between these two transitions, the intensity ratio between these two transitions should be 5:7 from the spin multiplet analogy. But in the molecular framework, where when the CS study has been done, they have shown a different picture. That is basically due to the different sp hybridization in the molecular orbital framework, where there is no pure s or p orbital, but spd hybridized orbital, and there is also this 3p 3d exchange interaction between the orbitals. So not only you will get a sharp peak around this k beta x ray emission spectrum, but also for the high spin iron system, as you can see in the figure, for the high spin iron transition metal complex, you will also get a solder around the sharp peak, which is coming from the ligand complexes. So we'll try to explain this thing with a theoretical model. So we have chosen our theoretical model as the IPUMCC method, which is ionization potential from the equation of motion coupled cluster singles and doubles approach. So single reference coupled cluster theory is known to give a very accurate results for the ground state, where you can see the Schrodinger's equation is written with the simply modified coupled cluster framework, where H bar is the similarity transformed Hamiltonian, where H bar is the exponential minus T, H exponential T, where T is the excitation operator which excites an electron from the occupied orbital to virtual orbital. So A and I are the creation and annihilation operator which expand the occupied space to the virtual space, and TIA are the amplitude of the singles excitation, and TIJAB are the amplitude of the doubles excitation manifold. So as I have told you earlier, the single reference coupled cluster theory is known to give you accurate result for the ground state. To capture the excited state, as we require here to capture the core ionized excited state, we will use a linear expansion of excitation operator which projects the ground state to the excitation manifold by a linear excitation operator R, where R we have taken R as the ionization operator which excites the electrons in the singles and doubles ionized manifold, where R is represented as Ri, which is the singles amplitude, and Rijb is the doubles amplitude. To solve the Schrodinger's equation, the modified Schrodinger's equation, we have to take the left projection with the appropriate excitation manifold, which will give us the exact ionization potential energy as the difference between the ground state and the ionized state as omega k. To solve this equation, we have taken the sigma vector approach. Since this UMCC method is non-symmetric eigenvalue, has non-symmetric eigenvalue, we have to solve for both the right vector and the left vector. So if we do that, by solving the right vector and left vector, we can move on to calculate the transition density matrix. So these are the orthogonality condition in the equation 6, as you can see, where L is the left eigenvector and R are the right eigenvector, and omega are the ionization potential of the excited states. So using this orthonormality condition, we solve the left vector and right vector, then we move on to calculate the transition dipole matrix. So as any operator in the left and right vector, we have to calculate the modulus of the transition density matrix. As you can see, since we are using the exponential ansatz, the dipole moment operator is also similarly transformed e to the power minus t d e to the power t, where d is simply the dipole moment operator between two states, whether it is a core hole state or an ionized excited state. So L and K are the different corresponds to different states. So if we calculate the transition density matrix between L state and K state between two orbital P and Q, then we can have the transition density matrix as given in equation 8, where EPQ are the excitation operator exciting an electron from the Q orbital to P orbital. So if we calculate the transition density matrix, then we are free to calculate the oscillator strength from the equation 9, and we can put that oscillator strength to the intensity which can be compared to the experimental spectrum. So to demonstrate our results, we have taken a series of molecules. So we have taken the methane chain system. So where we have taken the CH4 methane molecule as the start molecule, and then we will replace one hydrogen in each time with a fluorine atom. So the system of study is CH4, CH3F, CH2F2, CHF3, and then CF4. So as we all know, CH4 and CF4 belongs to the TD point group symmetry. Since this is a non-abelian symmetry group, we have taken in our computation the D2 point group symmetry. And for the CH3F and CHF3, C3V is the point group symmetry. Since this is also a non-abelian point group, we have to take in CS, and CH2F2 is a abelian symmetry group of C2V. So we have done the calculation with this symmetry group. So this is the molecular orbital picture. So CH4 is the simplest system here. Now where carbon 1s is ionized from the 1s orbital so when an electron from the core hole is ionized, an electron from the upper valence, that is sp3 hybridized orbital, tries to fill it up. Since this sp3 hybridized orbital give you 3 degenerate level, all the contribution from the sp3 hybridized orbital to C1s will be exactly same, and it will give you only one peak. So likewise, we have calculated also the CF4 molecule. So CF4 has a larger number of electrons and larger number of inner cells in between. So when an electron from the core hole of carbon 1s is ionized, then an electron from the upper valence cell tries to fill it up. But as you can see from the molecular orbital, the upper panel shows and the HOMO orbital, which is predominant pi orbital centered on fluorine atom. Okay, so this will not contribute. Contribute much to the C1s transition because it is centered on F. The next one is basically sp hybridized orbital centered on fluorine atom again. So it will have some contribution towards C1s because of the sp hybridized orbital. But since it is centered on fluorine, the contribution will be much less. The next one is a sigma centered orbital on carbon. Since from the dipole interaction we know S to S transition is not allowed, this contribution will again be very less. The most contributing factor from the molecular orbital will be this orbital, the last orbital, which is sp3 hybridized, and it is equally shared. The orbital is equally shared between carbon and fluorine. It will have the most significant contribution in the carbon 1s X-ray emission spectrum. So in the next slide, I have plotted all the X-ray emission spectrum. The other molecules CHF3, CH2F2, or CH3F are hard to explain in terms of molecular orbital, so we have to rely on the correctness of the calculation of the program package. So as you can see, as I said earlier, that CH4 only have one peak. So the dotted line corresponds to the experimental spectrum. The solid line corresponds to the theoretically computed spectrum. The bubble corresponds to the different oscillator strength from different states. So now we have actually normalized the highest peak and shifted the peak corresponds to the theoretical and experimental and matched all the results. So the error bar of our theoretical and experimental value are within 1 electron volt. So as you can see, the spectrum matches quite nicely, and we can also identify which state is contributing to which state. So this is the carbon 1s Kh X-ray emission spectrum. This is again the fluorine 1s X-ray emission spectrum, where states from different orbitals are contributing to the fluorine 1s Kh. This again, the experimental spectrum are nicely reproduced by the theoretical computation. So we have extended this approach to the other molecules also. Here you can see the benzene ring system, where one carbon is replaced by fluorine OH radical or NO2 system, and we have.
Excuse me, Dr. Abhijit Sen.
Yes,
as we are running little short of time, so if you can conclude.
Yeah, this is basically my last slide. This is basically my last slide. So you can see the results here. So with this, I would like to stop here. Just before that, I would like to acknowledge my PhD guide, Professor Debashish Mukherjee, and postdoc guide Frank Nize for their help and support, and currently Sam Prasad College for providing the current framework. Okay, thank you.
Okay, so thank you very much for his nice presentation. And now this session is open for some questions or comments from the audience, if there are any.
No, I can't see any questions.
Okay, so let us thank the speaker once again for his very nice presentation. And let me now go to the last presentation for this session.
Okay, thank you. And
okay, thank you, Dr. Shen. Thank you for your very nice talk. So the last presentation of this session is going to be delivered by Mr. Qazi Islam, our UG student of Adams University, Department of Physics. Qazi, can you hear us?
Yes, sir. Can you hear me?
Yes, we can hear you. We are very much interested to listen from you. So please share your talk.
Yes, sir. Can you see my screen?
Yes, Qazi, we can see your screen.
Yes, sir. Okay. Good morning, everyone. I'm Qazi Islam, and I'm in my first year pursuing BSc Honors in Physics. Today, I'm going to present a self-directed project of mine, and this project is about formulation of the problem of finding volume of n-sphere and obtaining an answer. So in order to subject the above idea to analysis, one must first obtain a precise analytical definition of n-sphere. So thus, let us first begin by defining what an n-sphere or sphere in high dimension means. So if you look at the two special cases which are available to us, the sphere, the defining property of sphere in 2 dimension and in 3 dimension is that it is basically the locus of all points that are the same distance from another point, which we generally call the center. So we know that in 2 dimension, the distance is given by square root of x squared plus y squared and square root of x squared plus y squared plus z squared in 3 dimensions. So if we equate them to a constant, we can define sphere in their respective dimensions. So now it is evident that we need to generalize a notion of distance in order to define a sphere in n dimensions. It is evident that if we had 2 points given by x1, x2, x3 till xn and y1, y2 to yn, then we can define a notion of distance dx, y as shown in figure 1.3. Now, however, naturally a question arises, which is that is this definition a valid notion of distance? We see that this already takes into account the special cases we discussed for 2 dimensions and 3 dimensions. However, if we want to answer the question more rigorously, what we have to do is we have to show that this distance measure satisfies the axioms of distance measure as shown in figure 1.4. This includes some basic properties we would like our distance measure to respect. For example, the fact that distance has to between 2 points has to always be greater than 0. Then the fact that distance between 2 points is 0 if and only if both are the same and identical points. Sufficient it is to say that this does respect all of the axioms. So we can use this as a valid notion of distance. So if you just equate to it to a constant and square it, we can obtain a definition for n-sphere as shown in figure 1.5. So now having already defined what an n-sphere is, let us now establish the problem statement. So now in order to find the volume of an n-sphere, we have to basically integrate over the region R, which is defined by the equation of n-sphere. And this is a multiple integral that we have to evaluate. So now the difficulty in the evaluation of the problem generally arises from the fact that the limits are very difficult to determine. In 2 dimensions and 3 dimensions, this difficulty is overcome by using polar coordinates and spherical coordinates. So this naturally motivates us to find the generalization of spherical coordinate transformation that could exploit the symmetry of our problem and make it easier to evaluate the integral. So thus we arrive at the subproblem of generalizing the spherical coordinates. So let us actually consider the n equals to 2 and n equals to 3 case and construct the spherical coordinates to gain an insight about how to generalize for to n dimensions. So on the left in figure 3.1, we have the n equals to 2 case, and we generally first begin by defining an angle θ1 with respect to the x1 axis, and we proceed by resolving the vector into its components, and we arrive at the results we want. Just note that θ1 ranges from 0 to 2 pi here, while r ranges from 0 to infinity. In the n equals to 3 case on the right, what we do is we first begin by defining an angle θ1 with respect to the x1 axis. Then first we consider its projection on the x1 axis, and then we consider its projection on the x2, x3 plane. Then we proceed exactly how we did for n equals to 2 case by defining an angle θ2 with respect to the x2 axis. Now, the question that I'm interested in asking is, can we actually do the 3-dimensional case without actually employing 3-dimensional visualization? Answering this will lead us to be able to proceed with construction of spherical coordinates in higher dimensions. So let us look at how we can think. This is just a heuristical way of doing the same thing that we saw previously. But I shall justify later on why whatever coordinate transformations I obtain from this heuristical method is justified. So what we do is we first construct x1, and then we consider x2, x3 conjointly as one plane. Then we simply resolve after defining the angle θ1 with respect to x1 axis, we simply resolve how we resolve. And on the x2, x3 plane, we see we have the resolved component as r sine θ1, which becomes the new radius for consideration when we split the x2, x3 axis into individual x2 and x3 axis. And then again, after defining the angle θ2, we resolve them into components. Now, this method of thinking actually seamlessly generalizes, and you can see the same I've done for 4 dimensions. So first I've considered x1 and the axis x2, x3, x4 conjointly. Then I've split that into x2 and x3, x4 conjointly. Then the last again recursively. So when you do this, you obtain a few results, which I shall show here. And from here, we can directly go to the generalized spherical coordinates. So what we have arrived is at our general spherical coordinates through mathematical induction from the patterns that we saw previously. Note that θ1 ranges from 0 to infinity, and θ2, θ3 all the way till θn-1 ranges from 0 to pi, and θn ranges from 0 to 2 pi. So how do we know that this is a valid generalization? Well, actually, to know that this is valid, to show that this satisfies the definition of n sphere that we came up with. And in fact, you can check it does indeed satisfy the definition. So we can proceed without any further complications. So now the evaluation of integral, we have to actually change the variables from x, which are Cartesian coordinates, to theta, generalized spherical coordinates. So a crucial notion when changing changing variables in multiple integral is the Jacobian. So let us actually examine it. So basically, whenever you're considering a transformation T from a coordinate system, say UV to XY, the areas and volumes get scaled up by an amount which is given by the Jacobian. So when you're changing, say, variables from Cartesian to spherical coordinates, then you have to multiply by this Jacobian factor as shown in the diagram here, so that to preserve the equality of the integrals before and after the transformation, you have to multiply the Jacobian factor here. So how do we actually compute the Jacobian? So as you can see in figure 4.3, the determinant of this matrix will give you the Jacobian, and the ith and jth, the element in the ith row jth column is given by taking the partial derivative of xi with respect to theta j, where xi is nothing but the spherical coordinates transformation that we have already discussed. Now, computation of this becomes quite tedious when you try to compute them out by hand. So I have used an algorithm to compute them out for me, and here are the results I have obtained. So the Jacobians till n equals to 6 dimensions are shown here, and from that we can easily conjecture a form which is shown in figure 5.6 to be the Jacobian for n dimensions. Now, having dealt with the Jacobian, let us come to the crux of the problem, which is to finally figure out the volume integration. So under the change of variables from Cartesian to spherical coordinates, we see that the problem statement then simplifies to the following after changing and accounting for the Jacobian. And we have to just put the limits in from 0 to r, 0 to pi, because I've already discussed the ranges from which theta 1, theta 2, and so on range from. So when you plug in those limits and you just do the following steps and simplify the integration, then you obtain the following form. So note that because out here theta 2, theta 3, and so on and so forth are just variables inside, dummy variables inside definite integration. So we can swap them out for phi and it won't change the answer. So the way we evaluate this form that we have obtained for the volume is by using the reduction of power identity that we are probably aware of. And then if you just consider the integral of 0 to pi of sine to the power of n x dx to be in, then we can use the recursive relationship as shown in 5.3 to obtain the values. So here are a few volumes that I have computed out. And these results match the ones that were obtained in literature as well. So actually, now is the final, let me come to the conclusion of and discuss some of the results. So here I've plotted the dimension n versus the volume of the n sphere. So from the graph itself, we can already see a few counterintuitive results. We see that, for example, the blue curve, which is a unit n sphere, you see there's a maximum which happens at around, I guess, n equals to 5. So basically, as you keep increasing the dimensions, when you reach n equals to 5, that's the point where you have the maximum volume, after which the volume starts to decrease. And what's also interesting is the fact that as you keep increasing n, as you tend n to infinity, the volume tends towards 0. So it is as if the higher you go in dimensions, the space that you have is shrinking in a certain sense. Also, because the smooth curve seems to reasonably fit the data that I've obtained here, you can reasonably answer the question of what is the volume of a sphere with dimensions, say square root of 2, or say what is the dimension of a sphere with dimension n equals 2.5. What is the volume of a sphere with dimension n equals 2.5, and so on. Also, what we see is that the peak value, which I was discussing, seems to shift as you increase the radius values. So these are the final results I've obtained. And so thank you for listening to me. And there were a lot of issues that I didn't go in detail with because of the time constraint. So if you're interested, you can get in touch with me. You can email me, or you can WhatsApp me on my contact number here. Thank you.
Thank you, Kazi. Thank you for your introduction and presentation to this particular problem. If there is any question, now it is open for questions or comments. Yes. Bimal sir, please ask your question. Kazi, can you hear me?
Yeah. Yes, sir, I can hear you. I think
Okay.
sir is muted.
Sir,
I can
please
see sir
unmute,
speaking.
sir.
Yes, Kaji,
Yes,
your
sir.
work really appreciable, really very nice. Please,
Thank you very much, sir.
you have thought something. Some question you have shown that when we are going from very low dimension to very high dimension,
yes,
the space consumed is less.
yes,
right?
Yes, yes.
Have you any kind of thought or in this process why it is going
Yeah,
so?
okay. I can give you a sense. I anticipated that I would have this question. So I can give you a sense of why, analytical sense of why the volume should kind of decrease. The fact is that when you look at the equation of a sphere, let's say in 3 dimensions, it's x squared plus y squared plus z squared is equals to a constant, radius square, basically. So when you choose, let's say, x equals to 0.5, the choices of y and z are constrained in such a way that it has to equal 1 at the end. So, but if I added another variable, let's say y squared plus z squared plus w squared, now that whatever was the remaining has to be distributed amongst these 3 variables. So they become less in turn. So what happens is, in a certain sense, as you go higher in dimensions, what happens is the points become closer in a certain way, which is why I suppose the space is getting constricted. Does that answer your question? Was I able to provide a reasonable?
Yes, actually, it's your explanation something. Just you are thinking something. So okay, we'll talk later also.
Yes, sir.
Yes. Yes. Okay. Thank you.
Okay, thank you, sir. So, do you have any other questions, sir, or is it okay? Any other questions from anyone?
I think there is no such question.
No such questions. Okay.
So let us thank the speaker, Mr. Kaji, once again. Thank you very much for your talk. And now this session is complete. This is the last session of this YPM 2023. So Tamal sir, please conclude this session.
Okay, thank you very much. So it was indeed a very pleasant and exciting online conference. So we have learned a lot, and there is a extensive discussions. So I would like to first thank our university administration for providing active support to organize this online conference. And I would like to especially mention our IT team for extending their help to arrange this conference online. And next, I would like to mention the dean of our school, Professor Bhattacharya, and also the head of the department of our head of the department, Dr. Momita De, and the organizing team, Dr. Swarup Niyogi, Dr. Papia Dhara, Dr. Shikha Das, Dr. Shatarupa Vishwas, Professor Somnath Chatterjee, and I'd like to also thank the esteemed speakers who have contributed to this conference, and last but not the least, our audiences for their active participation in the discussion session. So with this, we come to an end. So have a nice weekend. Thank you very much.
Thank you, Tamal sir. So now I request Papia to take over the session.
Thank you so much. It was really nice session, and what I want to say at the last, that you always with us, all the participants, and what I can only attribute this success to your constant involvement, and hope that next year or for any upcoming event you will be with us only. So thank you so much. And another important information, that for the invited speakers, you will receive your certificate after some days. We will contact you through mail. And already I have shared the participation certificate link, so you may fill it. It will be automatically generated. Thank you so much, everybody.
Yes, thank you so much from
And
our
also,
side.
I'd like to mention one thing I missed. Dr. Purva Bhattacharya, she was from start to end was involved in organizing this conference
Yes.
actively. So thank you very much, Purva.
So
our HOD madam is here, so if you want to say something.
Thank you, Papia. I think everybody has said thanks, and there's nothing new that I can contribute. But yeah, finally, my sincerest thanks to Dean Sir and Vice Chancellor and everyone else for giving us the permission to do this event right before the interim examination. And at the same time, I'm very much grateful to all the speakers, all the participants, all the students who have spent their Saturday by listening to all the talks. Thank you so much. And thank you, special thanks to you and Sharup and Diptoshika for this wonderful arrangement. Thank you.
Thank you so much.
Thank you.
So before closing this session for today, I would like to request, because some participants are already present in this online mode. So if there is any suggestion from your end to our organizing team, so that we can incorporate it, and in future, whenever we will conduct YPM 3, this is YPM 2. When we will conduct YPM 3, we will try to incorporate all those things. So if there is any comments from your end, please share with us. Otherwise, as Papia Madam has mentioned that she will share the feedback. She has already shared the link. There is also the opportunity to give feedback. And so please give your feedback so that we can improve our, from our end, we can improve our organization. We can also organize similar kind of events in future. So thank you very much from my side. So Diptoshika, if you wish to say, please.
Yeah, actually, thanks to all the participants for joining us, and I hope that you all enjoyed all the sessions of the seminar. And definitely, if you have some suggestion, please share with us so that we can improve next time. So thank you all.
Okay. So, Dr. Papia Dhara, can we now, in a position of final conclusion, we can end the session?
Papia, you are on
muted. Yeah.
Awesome. We can end the session. Obviously, we can end this journey, this short journey of YPM 2023. But with the hope that we will meet again, and hope in our next event, maybe in conference or this kind of seminar. So with this thought, obviously, we can say goodbye for now. Have a nice day ahead, and best wishes to all of you. Have a nice day.
Thank you very much.
Thank you so much.